What if everything you thought you knew about the universe was just the tip of an infinite iceberg? Imagine staring into the night sky, marveling at the stars, and realizing that behind their brilliance lies a multitude of questions that could shatter our understanding of reality. From the invisible forces pulling entire galaxies to the unexplainable energy driving the universe to expand faster than ever, the cosmos is a playground of mysteries that scientists are still struggling to decipher. In this video, we are taking you on an awe-inspiring journey through 50 of the most perplexing cosmic enigmas, questions so big and bold that they make us feel both incredibly small and immensely curious. The deeper we explore, the more we uncover, yet the answers seem to stay just out of reach. Buckle up, because this adventure will stretch your imagination, challenge everything you thought you knew, and leave you with a sense of wonder that only the vast, unyielding unknown of space can provide. Are you ready to uncover the mysteries of a universe that refuses to give up all its secrets? Let's dive in. Now, turning to one of the most puzzling enigmas of the cosmos, let us explore the Great Attractor, a gravitational anomaly so immense that it is pulling entire galaxies, our own Milky Way included, toward it at incredible speeds. Hidden behind what scientists call the zone of avoidance, a region of the sky obscured by the thick clouds of dust and stars in our galaxy, the Great Attractor is shrouded in mystery. Despite being largely invisible to us, its gravitational influence is undeniable, steering massive clusters of galaxies on a collision course toward an unseen destination. But what exactly is it? Some scientists speculate that it could be an unimaginably large cluster of galaxies hidden from our view, while others believe it might be a concentrated mass of dark matter, the elusive substance that makes up much of the universe yet remains undetectable except through its gravitational effects. Still, the true nature of the Great Attractor continues to elude us. Why is it there, and what could it reveal about the large-scale structure of the universe? This cosmic phenomenon serves as a humbling reminder of how much remains beyond our grasp, teasing us with the possibility of a deeper, hidden architecture of the cosmos yet to be discovered. With so much speculation and so few answers, the Great Attractor continues to baffle scientists and ignite our curiosity about the mysteries lurking just out of reach. Moving forward, there's another invisible force that demands our attention, one that shapes the universe in ways we are only beginning to understand. Moving forward, let us unravel the perplexing concept of dark matter, an invisible substance that makes up roughly 27% of the universe, yet completely evades direct observation. Unlike stars, planets, or gas clouds that emit or absorb light, dark matter does neither. So, how do we know it exists? The evidence lies in its gravitational effects. For instance, when scientists study the rotation of galaxies, they find that the outer regions spin at speeds far greater than what visible matter alone can account for. This peculiar observation suggests the presence of an unseen mass exerting additional gravitational pull. Another compelling clue comes from gravitational lensing, a phenomenon where light from distant galaxies is bent as it passes through massive objects. The degree of bending often indicates the presence of far more mass than we can visibly detect. But what exactly is dark matter? Some theories point to exotic, weakly interacting particles that slip through ordinary matter without leaving a trace. Others propose it could consist of primordial black holes formed in the earliest moments after the Big Bang. Yet, despite decades of investigation, no direct detection has been achieved, leaving dark matter as one of the most tantalizing cosmic enigmas. Its true nature continues to challenge and inspire scientists, as understanding it could unlock fundamental secrets about the universe's structure and evolution. With dark matter's mystery still unsolved, we now turn to an even larger puzzle, the force that might explain why the universe is not just expanding but doing so at an accelerating pace. With the next phase of the journey in sight, let us delve into the mysterious force known as dark energy, a phenomenon even more baffling than dark matter. Imagine this: the universe is not only expanding but doing so at an accelerating rate, as if there were a hidden energy pushing galaxies apart faster and faster. This strange behavior was first discovered in the late 1990s when scientists observed distant supernovae, exploding stars that act as cosmic milestones. They found these supernovae were dimmer than expected, indicating that the universe's expansion was speeding up over time rather than slowing down as once assumed. Dark energy is thought to be the driving force behind this acceleration and is believed to make up a staggering 68% of the universe. But what exactly is it? That is where the mystery deepens. One possibility is the cosmological constant, an idea first proposed by Albert Einstein to describe a uniform energy density inherent to space itself. In this view, as space expands, new space is created, and with it more dark energy, leading to perpetual acceleration. Another intriguing theory suggests quintessence, a dynamic, evolving field that changes in strength over time, unlike the cosmological constant, which remains unchanging. Yet, both theories face significant challenges, as scientists have no direct way of measuring or detecting dark energy, leaving its true nature shrouded in uncertainty. The implications of solving this puzzle cannot be overstated. Understanding dark energy could fundamentally alter our knowledge of physics, space, and the ultimate fate of the universe. Will the universe expand forever in a state of eternal cold and isolation? Could the acceleration eventually reverse, leading to a cosmic collapse, or might space itself tear apart in a catastrophic event known as the Big Rip? These questions linger as some of the most profound in modern science, with dark energy presenting challenges that reshape our understanding of the cosmos. Let us now explore the mysteries surrounding the very beginning of the universe itself. With the next phase of the journey in sight, let us explore the mysteries surrounding the beginning of the universe, an origin story that continues to baffle even the sharpest minds in science. Picture this: the universe in all its vastness, once existing as a singular point, unimaginably dense and extraordinarily hot. Then, approximately 13.8 billion years ago, in an event we now call the Big Bang, this point expanded, giving rise to the cosmos as we know it. But what triggered this incredible moment of creation? And perhaps an even more perplexing question: what came before it? Scientists have worked tirelessly to uncover the answers, but concrete evidence remains frustratingly elusive. Some theories suggest that the Big Bang itself may have been the result of quantum fluctuations, minute changes in energy at the smallest scales, which could have sparked the expansion of that primordial point. Others propose the idea of the multiverse, where our universe is just one of countless others that continually form and evolve, each with its own physical laws and initial conditions. This raises the tantalizing possibility that the Big Bang may not have been the absolute beginning, but rather a chapter in an ongoing cosmic cycle or multiversal narrative. Yet, these ideas come with their own challenges. Quantum mechanics, which governs the very small, and general relativity, which explains the behavior of massive objects like galaxies, clash when applied together to these early moments, leaving scientists without a unified framework to fully describe what happened. Complicating matters further, the extreme conditions of the Big Bang leave little hope of ever directly observing or recreating its earliest moments. Despite these limitations, studying the first moments of the universe through techniques like analyzing the cosmic microwave background radiation, which acts as a faint afterglow of the Big Bang, has provided tantalizing clues. However, these clues only take us so far, and many fundamental questions remain. Was there truly a before the Big Bang, or does the concept of time itself break down at this singular event? Could the universe have emerged from nothingness, or is there an eternal cycle of birth, death, and rebirth? As we ponder these profound questions about our cosmic origins, let us now look ahead to the other side of time and unravel the mysteries surrounding the ultimate fate of the universe. As the next challenge unfolds, we journey to the other end of time and confront the mysteries surrounding the ultimate fate of the universe. While the beginning of the cosmos sparks questions of origin, its eventual end raises equally profound uncertainties. Theories abound, each painting a vastly different picture of how everything we know might cease to exist. One prominent idea is the Big Freeze, a future where the universe continues to expand indefinitely. Over countless trillions of years, galaxies would drift further apart, stars would burn out, and all matter would decay into a cold, dark void. In this scenario, the universe becomes a vast expanse of nothingness, stripped of energy and life, a chilling end to everything. Equally compelling is the theory of the Big Crunch, which suggests the opposite fate. Here, the expansion of the universe would reverse, causing galaxies to collide and compress back into an incredibly dense hot point, potentially setting the stage for another Big Bang. This cyclical model raises the intriguing possibility of endless universes being born and reborn in an eternal cosmic loop. And then there's the Big Rip, perhaps the most dramatic of the theories. In this scenario, if the mysterious force of dark energy continues to accelerate the universe's expansion, it could eventually overcome all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. The universe would essentially be shredded into its most basic components, leaving behind a chaotic, fragmented void. But which, if any, of these possibilities will come to pass? The uncertainty lies in our limited understanding of dark energy, the elusive force driving the universe's accelerated expansion. Despite making up the majority of the cosmos, its true nature remains one of the greatest puzzles in cosmology. Complicating the matter further, recent observations have revealed conflicting data about the rate of this expansion, a mystery scientists call the Hubble tension. These uncertainties leave us without a definitive answer, highlighting just how much remains unknown about the universe's ultimate destiny. Whatever the outcome, pondering the end of the cosmos reminds us of the transient nature of existence and the sheer scale of the universe's mysteries. With this in mind, let us turn our gaze toward another profound enigma, the question of why, in a universe teeming with stars and planets, we have yet to find evidence of extraterrestrial life. Now turning to the Fermi Paradox, we are faced with one of the most thought-provoking questions in all of astronomy. If the universe contains billions of stars and likely even more planets, why haven't we found evidence of extraterrestrial life? This puzzle arises from the apparent contradiction between the high probability of life elsewhere and the complete lack of solid evidence for it. One of the most popular explanations is the concept of the Great Filter, which suggests that somewhere along the progression from simple life forms to advanced civilizations, there exists a nearly impossible hurdle. This filter could be in our past, meaning that developing intelligent life is incredibly rare, or it might lie in our future, indicating that advanced civilizations may inevitably collapse before they can make themselves known. Another possibility is that intelligent life is out there but deliberately avoiding contact. Advanced civilizations might camouflage themselves, either for fear of hostile species or to avoid disturbing less developed ones, just as we take care not to interfere with the natural environment of animals on Earth. This raises the unsettling question of whether we are the ones being observed from afar. Alternatively, the answer may lie in our own limitations. Perhaps our technology is simply not advanced enough to detect the signals or signs of extraterrestrial life, or we are looking in the wrong ways or places. What if communication methods used by advanced civilizations are so sophisticated that they bypass the kinds of signals we know how to identify? The Fermi Paradox challenges us to reconsider our assumptions about life, intelligence, and contact in the vastness of space. It reminds us of how much we still have to learn and leaves us to wonder, could the silence of the cosmos be hiding something astonishing? With these possibilities in mind, let us explore another cosmic riddle. Could some civilizations leave behind monumental structures to harness the energy of their stars? Now turning to the fascinating concept of Dyson spheres, we are introduced to an idea that feels plucked straight from science fiction but is grounded in theoretical science. Imagine a civilization so advanced that it constructs a colossal structure entirely surrounding its star, capturing nearly all of the energy the star emits. This groundbreaking idea was proposed by physicist Freeman Dyson, who envisioned such megastructures as a logical step for a highly developed civilization seeking to meet its immense energy needs. A Dyson sphere would revolutionize how energy is utilized, theoretically powering technologies beyond anything we can currently imagine. Yet, despite combing through the cosmos with advanced telescopes and data analysis, we find no trace of these energy-gathering megastructures. Could this mean that no civilization has reached such an advanced stage, or are we simply not recognizing the signs? One theory suggests that some advanced civilizations may choose not to build Dyson spheres at all, instead opting for more subtle technologies or strategies that leave no detectable footprint. Others propose that we might be looking in the wrong way after all. A complete Dyson sphere could block out a star's visible light and emit energy in infrared wavelengths instead, a signature that might be easy to overlook in the vastness of space. Another possibility is that constructing such an ambitious project could be so resource-intensive that civilizations decide it is not worth the effort, or perhaps the civilizations capable of building Dyson spheres reach a singularity or collapse before completing such endeavors. This absence of evidence raises deeper questions about the nature and behavior of intelligent extraterrestrial life, and whether our methods of searching reflect the limitations of our own understanding. Dyson spheres remain one of the many tantalizing mysteries that push the boundaries of our curiosity about the universe. With that, let us dive into yet another cosmic enigma, the brief yet powerful signals known as fast radio bursts. Moving forward, we encounter one of the most puzzling phenomena in modern astrophysics: fast radio bursts, or as they are commonly referred to, intense flashes of radio signals originating from the depths of space. These bursts are incredibly brief, lasting mere milliseconds, yet within that fleeting moment, they release an amount of energy equivalent to what the sun emits over several days. The first of these enigmatic signals was discovered in 2007, setting off a wave of excitement and speculation within the scientific community. What makes fast radio bursts so captivating is not only their power but also their mysterious origins. Scientists have pinpointed some of these bursts to specific galaxies billions of light years away, yet the exact cause behind them remains uncertain. Some theories suggest that the powerful magnetic fields of neutron stars, also known as magnetars, could be responsible, as they are capable of producing such energetic bursts. However, not all fast radio bursts fit the characteristics expected from magnetars, leaving room for alternative explanations. Could they be a byproduct of some unknown cosmic event, or perhaps even signals stemming from advanced extraterrestrial civilizations attempting to communicate across the universe? The sheer irregularity of these bursts adds another layer of intrigue. Some fast radio bursts are one-time events, while others, called repeaters, have been observed to emit bursts multiple times from the same source. This inconsistency in behavior only deepens the mystery, as it could hint at multiple types of origins. Adding to the complexity is the vast distance between us and these bursts, which makes gathering detailed data a daunting task. Deciphering fast radio bursts is like trying to piece together a puzzle with much of the picture still hidden. Despite significant advancements in technology and methodologies, they remain one of space's most baffling riddles, driving scientists to continue their search for answers. As we delve deeper into the unknown, these fleeting signals challenge our understanding of the universe and spark endless curiosity. Speaking of mysteries that defy easy explanations, let us now shift our focus to the peculiar case of the Pioneer anomaly. Now turning to the puzzling phenomenon known as the Pioneer anomaly, we delve into an enigma that has perplexed scientists since its discovery in the late 20th century. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s to explore the outer solar system, achieved remarkable milestones, including becoming the first human-made objects to journey beyond the known planets. However, as they ventured farther into deep space, something unexpected began to happen. Both spacecraft exhibited a tiny but consistent slowing in their trajectories, a deviation that could not be explained by the known forces acting upon them. This subtle deceleration, though minor, amounted to a measurable discrepancy over vast distances, sparking an intense debate among physicists and engineers alike. One of the leading theories attributes the anomaly to heat emissions from the spacecraft themselves. The idea is that as the onboard systems generated heat, particularly from their power sources, the photons emitted in one direction might have created a small but steady push in the opposite direction, slightly altering their course. While this explanation aligns with principles of thermodynamics, it remains difficult to confirm definitively due to the sheer complexity of deep space environments and the challenges of reconstructing data from spacecraft that are now billions of miles away. Alternatively, some researchers have proposed that the Pioneer anomaly could point to more groundbreaking possibilities. Could it be evidence of new physics, such as a previously undiscovered force or a subtle modification to the laws of gravity that only becomes apparent over immense distances? Such theories, while speculative, highlight the tantalizing potential for deep space exploration to reveal phenomena beyond our current understanding of the universe. To further complicate matters, the anomaly has not been observed in other spacecraft to the same extent, raising questions about what unique factors could affect the trajectories of Pioneer 10 and Pioneer 11. It is possible that their specific design, mission path, or even distant gravitational influences could play a role, but no single explanation has resolved all aspects of the mystery. As scientists continue to analyze historical data and develop more advanced models, the Pioneer anomaly serves as a reminder of how even the most well-planned missions can yield unexpected results. It underscores the boundless curiosity that drives humanity's quest to understand the cosmos, where every unanswered question could lead to profound discoveries. With this intriguing mystery in mind, let us now venture into the extraordinary and abrupt phenomenon known as the Kuiper Cliff. With the next phase of the journey in sight, we arrive at the Kuiper Cliff, a peculiar feature at the edge of our solar system that has left scientists scratching their heads. The Kuiper Belt, a vast region of icy bodies orbiting beyond Neptune, is home to countless small celestial objects, including dwarf planets like Pluto and Haumea. For decades, astronomers believed this region gradually thinned out as one moved farther from the Sun. However, upon closer observation, they discovered something far more striking: a sudden and dramatic drop in the number of objects beyond a certain distance, a phenomenon now known as the Kuiper Cliff. The abruptness of this boundary is puzzling. Why does the solar system seem to taper off so sharply at this specific point rather than fading out gradually as expected? One hypothesis suggests that the regions beyond the Kuiper Cliff may have been cleared out by the gravitational influence of an unseen massive object. This has fueled speculation about the existence of a distant, hidden world, often referred to as Planet X, potentially lurking in the far reaches of our solar system. If such a planet exists, its gravitational pull could explain why this region appears so devoid of smaller bodies, as it might have either ejected them into interstellar space or drawn them into itself over billions of years. Yet the mystery does not end there. Some scientists have proposed that the Kuiper Cliff might indicate a limitation in the process of planetary formation itself. Beyond this distance, the Sun's gravitational influence weakens significantly, and the icy material needed to form large objects becomes increasingly sparse. This could mean that the cliff marks a natural limit where planets and smaller bodies simply could not coalesce in significant numbers. Alternatively, the cliff might be a relic of ancient interactions with other stars. In the early days of the solar system, our sun likely formed within a dense stellar cluster, where close encounters with neighboring stars were far more common. These gravitational interactions could have stripped away material from the outer edges of the Kuiper belt, leaving behind the stark boundary we observe today. Despite these intriguing theories, no definitive explanation has emerged to fully account for the Kuiper cliff. Current technology limits our ability to observe this distant region in detail, and new missions or advanced telescopes may be required to uncover its secrets. Until then, the Kuiper cliff remains a striking reminder of how much we still have to learn about the outskirts of our own cosmic neighborhood. As we journey onward, let us turn our attention to one of the most debated topics in modern astronomy, the elusive Planet X. Now turning to the mystery of Planet X, often called the ninth planet, we delve into the enigma that has fascinated astronomers for years. Planet X is theorized to be a massive, hidden world residing far beyond Neptune in the icy depths of our solar system. The intrigue surrounding this hypothetical planet stems from peculiar gravitational anomalies observed in the orbits of certain trans-Neptunian objects, small, icy bodies that orbit far from the Sun. These objects exhibit unusual clustering in their trajectories, as though they are being influenced by the gravitational pull of a large, unseen body. This observation has led many scientists to propose that a planet several times the mass of Earth might be exerting its influence from an extraordinary distance. The evidence for Planet X is compelling but indirect. Mathematical models and computer simulations suggest that the clustering of these distant objects is unlikely to be a coincidence. Instead, it points to the presence of a massive object shepherding their orbits over billions of years. If Planet X exists, it could be orbiting the Sun at a distance so vast that it takes tens of thousands of years to complete a single revolution, making it incredibly difficult to spot with current technology. Further fueling the search for Planet X are its potential implications for our understanding of the solar system's history and structure. If discovered, this mysterious giant could provide answers to long-standing questions about the formation and evolution of planetary systems. It might also help explain phenomena like the Kuiper cliff, as its gravitational pull could account for why the solar system seems to end so abruptly beyond a certain point. Despite numerous efforts to locate Planet X, its elusiveness remains a significant challenge. Its extreme distance means it would reflect very little sunlight, making it exceptionally dim and nearly impossible to detect even with powerful telescopes. Furthermore, its position in the sky is unknown, requiring meticulous and time-consuming searches of vast regions of space. While some scientists remain skeptical, believing the observed anomalies might have alternative explanations, the hunt for Planet X continues to push the boundaries of our observational capabilities. This ongoing quest underscores the dynamic nature of astronomy, where new discoveries often hinge on perseverance, advanced technology, and a bit of cosmic luck. As we await further breakthroughs, the mystery of Planet X serves as a humbling reminder of how much of our own solar system remains uncharted. Moving forward, we turn our attention to one of the most intriguing signals from the cosmos, a singular event that has puzzled researchers for decades, the enigmatic wow signal. Now turning to the enigmatic wow signal, we arrive at one of the most fascinating moments in the search for extraterrestrial intelligence. Detected in the year 1977 by a radio telescope at Ohio State University, this mysterious signal lasted a mere 72 seconds but left an impact that has endured for decades. The signal was so striking that astronomer Jerry Amon, who discovered it while reviewing data, wrote the word "wow" in the margins of his records, giving the event its memorable name. What made the WOW signal extraordinary was its intensity and frequency, which suggested it came from a precise and narrow band of radio waves, exactly the kind of signal researchers had theorized advanced civilizations might use for communication. Adding to its intrigue, the signal appeared to originate from the direction of the constellation Sagittarius, yet no natural source in that vicinity has ever been identified as a plausible explanation. Despite its significance, the WOW signal has never been detected again, leaving scientists with more questions than answers. Could it have been a one-time transmission from an advanced alien civilization, a fleeting cosmic event, or simply an Earth-based anomaly that mimicked the characteristics of an extraterrestrial signal? The inability to replicate or verify the WOW signal makes it a scientific deadlock, as researchers have no way to test hypotheses or gather additional data. Efforts to re-examine the same region of the sky have yielded no comparable signals, deepening the puzzle. Complicating matters further is the overwhelming challenge of distinguishing potential alien signals from the constant noise of natural cosmic phenomena and human-made interference. Space is brimming with radio waves emitted by stars, galaxies, and even Earth's own technology, making it like searching for a single whisper in a roaring crowd. While advanced algorithms and improved technology have made modern searches more sophisticated, identifying signals with the same unique qualities as the WOW signal remains exceedingly rare. Some researchers speculate that the signal, if artificial, might have been a deliberate message aimed at Earth, or perhaps just a faint leakage from an alien civilization's communication system. Others consider the possibility that we might have misinterpreted its origin altogether. The WOW signal continues to represent the tantalizing potential for discovering intelligent life beyond our planet, while also illustrating the immense difficulty in confirming such discoveries. It serves as a reminder that the universe, vast and mysterious, holds secrets that may take generations to uncover. With this remarkable signal as our guidepost, we now shift to another celestial enigma, a star whose bizarre dimming patterns have sparked conversations about the possibility of alien megastructures. Now turning to the mystery of Tabby's star, we encounter a cosmic puzzle that has mesmerized astronomers and sparked fascinating debates. Officially named KIC 8,462,852, this star gained fame due to its irregular and drastic dimming patterns, unlike anything observed in typical stellar behavior. First brought to public attention by astronomer Tabitha Boyajian and her team, the star's erratic dimming, sometimes by as much as 22%, has defied easy explanation. While most stars exhibit brightness fluctuations caused by predictable phenomena, the variations in Tabby's star are highly irregular both in timing and magnitude. This has led to wide-ranging theories about what could be causing these strange light fluctuations. One of the most attention-grabbing ideas is the possibility of alien megastructures, such as a partially constructed Dyson sphere. A Dyson sphere is a hypothetical structure that an advanced civilization might build around a star to harness its energy output. If aliens were indeed constructing such a colossal project, it might block the star's light in sporadic and irregular ways, resulting in the kind of dimming patterns observed. However, as captivating as this idea is, scientists have not found any other compelling evidence to support the existence of such megastructures in this case. More conventional explanations focus on natural phenomena. One leading theory suggests that a massive swarm of comets or a dense dust cloud might be the culprit, temporarily obscuring the star's light. However, even these scenarios encounter significant challenges. For example, a cloud of comets large enough to account for the dimming would be extraordinarily unusual, and no direct evidence of such an object near Tabby's star has been detected. Similarly, dust clouds would need to have highly specific properties to create such unpredictable dimming patterns, which raises further questions about their origin and nature. Adding to the intrigue is the fact that the star's brightness appears to have gradually decreased over the past century, a phenomenon that remains equally unexplained. This long-term dimming trend complicates efforts to pinpoint a single cause, as it suggests the involvement of processes that operate on both short and extended timescales. Some researchers have proposed that Tabby's star might simply be an outlier in our understanding of stellar physics, potentially representing a type of star with behavior we've never encountered before. Despite extensive observations and analysis, Tabby's star remains an enigma. The lack of a definitive explanation leaves the scientific community grappling with possibilities that range from the mundane to the extraordinary. It is a reminder of how much we still have to learn about the cosmos and how seemingly ordinary stars can surprise us in extraordinary ways. With this enduring mystery in mind, let us move forward to another perplexing question that cuts to the very fabric of our universe, the shape of the cosmos itself. Moving forward to the question of the shape of the universe, we dive into a profound mystery that lies at the heart of cosmology. Is the universe flat like an endless sheet of paper, spherical like a giant three-dimensional bubble, or something entirely beyond our intuitive grasp? This question has long fascinated scientists because the shape of the universe is not just a geometric curiosity. It directly influences the fate and behavior of everything within it, from galaxies to cosmic expansion itself. To tackle this enigma, researchers have turned to one of the most important pieces of evidence in modern astronomy, the cosmic microwave background radiation. The cosmic microwave background radiation is the faint glow of energy left over from the Big Bang, essentially a snapshot of the universe when it was just 380,000 years old. By studying this relic radiation, scientists have been able to measure tiny fluctuations in temperature that provide clues about the universe's large-scale structure. These fluctuations are like fingerprints, hinting at whether space curves inward, outward, or not at all. According to data from missions like the Planck Space Observatory, the evidence so far suggests that the universe is remarkably flat within an error margin of less than 1%. But here is where the mystery deepens. A flat universe is strongly tied to the concept of inflation, the rapid expansion that occurred fractions of a second after the Big Bang. While inflationary models align well with observations, they also lead to questions about why the universe's geometry appears so finely tuned, almost as if by design. Even more perplexing is the possibility that the universe might not have a single shape at all. Some theorists propose that it could be flat on observable scales, but take on a different geometry when viewed in its entirety. This aligns with the idea that what we perceive as the universe may only be a tiny part of a far larger and possibly infinite cosmos. Adding to the intrigue, certain models of quantum gravity suggest that space-time itself might be more fluid or dynamic than our current understanding allows, further complicating the effort to define the universe's true shape. What makes this cosmic puzzle even more challenging is the limitation of our observational reach. We can only study what lies within the observable universe, a sphere about 93 billion light-years across. Beyond this boundary, light from distant regions has not yet had time to reach us, meaning any conclusions about the universe's overall shape rely on indirect evidence. This leaves room for theoretical possibilities that include shapes we might not yet have the tools or concepts to comprehend. The shape of the universe represents one of the biggest unanswered questions in cosmology, blending cutting-edge physics with profound philosophical implications. It challenges us to consider not only the nature of the cosmos but also the limits of human understanding. As scientists continue to gather data and refine their models, we are inching closer to answers, but for now, the ultimate geometry of our universe remains one of the grandest mysteries of all. And with this captivating question in mind, let us journey further to another fundamental enigma of the cosmos, the mysterious absence of antimatter. Now turning to the enigma of antimatter, we confront one of the most perplexing questions in the story of the universe. Why is there so little antimatter when the Big Bang should have created equal amounts of matter and antimatter? According to our best understanding of physics, the birth of the universe was a perfectly symmetrical event. For every particle of matter produced, a corresponding particle of antimatter should have emerged. When matter and antimatter come into contact, they annihilate each other in a flash of energy. This means that if the universe began symmetrically, there should be nothing left today but radiation. Yet here we are, living in a universe teeming with matter and almost completely devoid of antimatter. This apparent imbalance defies explanation and represents one of the deepest mysteries in cosmology. Scientists refer to this conundrum as the Barrian asymmetry problem. To solve it, they have proposed various theories involving subtle differences in the behavior of matter and antimatter, collectively known as charge parity violation. In laboratory experiments, certain particles have shown slight deviations in how they decay depending on whether they are particles of matter or antimatter. While these findings are fascinating, the observed effects are nowhere near large enough to account for the overwhelming dominance of matter in the universe. This raises the tantalizing possibility that there are unknown forces or interactions at play, hiding beyond the reach of current experiments. Some researchers speculate that the answers might lie in the infancy of the universe, during a fleeting moment when extreme temperatures and densities allowed for processes that no longer occur. Others suggest that antimatter might not be missing at all but could be hiding in plain sight, perhaps concentrated in distant regions of the cosmos where massive amounts of radiation might betray its presence. However, extensive searches for antimatter in cosmic rays and distant galaxies have so far come up empty, leaving this theory unconfirmed. What makes the missing antimatter mystery even more compelling is its broader implications for our understanding of the laws of physics. If we can unravel why the universe is so skewed in favor of matter, it might reveal entirely new principles or particles that extend beyond the current standard model of particle physics. This could ultimately reshape our view of the universe itself and open up new pathways for exploring its origins. The scarcity of antimatter is not just a scientific puzzle, it is also a reminder of how fragile and improbable our existence truly is. Without this imbalance, stars, planets, and life as we know it would never have come into being. It is one of those cosmic mysteries that turns our gaze inward, forcing us to grapple with the question of why anything exists at all. As scientists continue their quest to uncover the truth, let us take another step on our journey and delve into one of the most energetic phenomena in the universe, gamma-ray bursts. Moving forward, we encounter one of the most staggering displays of cosmic power ever observed, gamma-ray bursts. These awe-inspiring explosions unleash more energy in just a few fleeting seconds than our Sun will generate over its entire lifespan of billions of years. First detected in the 20th century, gamma-ray bursts remain one of the most mysterious and intense phenomena in the universe, captivating scientists with their sheer scale and enigmatic nature. Most gamma-ray bursts are thought to occur when massive stars collapse under their own weight, forming black holes and blasting out ultra-high energy radiation in tightly focused beams. These bursts are often detected far across the cosmos, signifying cataclysmic events in distant galaxies. Yet, the origins of gamma-ray bursts are not fully understood. While the collapse of giant stars explains many of these bursts, other types, shorter ones, lasting just fractions of a second, are believed to result from the violent mergers of neutron stars. These dense remnants of dead stars collide with unimaginable force, creating shockwaves that ripple across space-time. However, even these explanations leave gaps in our understanding. For instance, what processes within these collisions or collapses produce such extraordinarily focused and intense energy emissions? Scientists are still unraveling how these events channel so much power into such narrow beams. Adding to the enigma, gamma-ray bursts challenge our observational capabilities. Because their energy output is so immense and brief, these bursts are nearly impossible to predict, and catching one in real time requires unparalleled precision. Despite advances in technology and space-based telescopes, countless bursts have occurred beyond the reach of human observation, leaving us to piece together an incomplete picture. Moreover, gamma-ray bursts can occur in regions of space where cosmic dust obscures our view, further complicating efforts to fully understand them. What makes gamma-ray bursts even more fascinating is their potential role in shaping the universe itself. It is theorized that these powerful explosions could influence galaxy formation, sterilize regions of space, or even trigger the creation of heavy elements crucial for life. Yet, the destructive force of a nearby burst would obliterate any chance of life on surrounding planets, underscoring their dual nature as both creators and destroyers in the grand cosmic tapestry. As scientists probe deeper into the universe's most violent phenomena, gamma-ray bursts serve as a reminder of how much we have yet to uncover. They are a testament to the sheer extremes of the cosmos, where forces beyond comprehension reshape the fabric of existence. As we stand on the brink of understanding their secrets, let us turn to another enigmatic feature of the universe, a peculiar cold region in the fabric of spacetime that has left scientists puzzled for decades: the cosmic microwave background cold spot. Now turning to the next cosmic enigma, we find ourselves peering into the faint but revealing afterglow of the universe's infancy, the cosmic microwave background, often simply called the CMB. This radiation, a remnant of the Big Bang itself, provides a snapshot of the universe as it existed nearly 14 billion years ago, offering insights into its origins and its early conditions. But amidst this ancient backdrop lies a perplexing anomaly that has left scientists scratching their heads for decades: the cold spot. This giant region of space appears significantly cooler than its surroundings, defying the otherwise remarkably uniform temperature of the CMB. First discovered in the early 21st century through satellite data, the cold spot spans hundreds of millions of light years, stretching the limits of our understanding. What makes the cold spot so mysterious is not just its size, but also the difficulty in explaining its existence. Some scientists propose that it could be a statistical fluke, a random irregularity that just happens to stand out in an otherwise consistent landscape. However, the improbability of such a large and distinct region arising by chance has led others to consider far more exotic possibilities. One daring hypothesis suggests that the cold spot could be evidence of a collision between our universe and another, a tantalizing hint at the possible existence of a multiverse. According to this idea, during the early moments of cosmic inflation, when the universe expanded at an exponential rate, our universe might have brushed up against a neighboring one, leaving behind this anomalous imprint. Another theory posits that the cold spot could be linked to a massive void, a vast region of space containing far fewer galaxies, stars, and matter than the surrounding areas. Such a void would affect the light traveling through it, stretching and dimming it, which could help explain the cold spot's cooler appearance. Yet, even this explanation raises questions about how such an immense void could form in the first place. It challenges current models of cosmic structure and forces astronomers to rethink the dynamics of matter on the grandest scales. What is perhaps most compelling about the cold spot is how it pushes the boundaries of modern physics. It forces us to question whether our understanding of the universe is incomplete, whether there are hidden forces or realities that we have yet to uncover. If the cold spot indeed represents a collision with another universe, it could open the door to an entirely new realm of cosmic exploration, hinting that our universe is just one of many. On the other hand, if it turns out to be a statistical coincidence or the result of some known process, it still serves as a reminder of the complexity and intricacy of the cosmos. As scientists continue to study this puzzling anomaly with ever more advanced tools, they inch closer to unraveling its secrets, hoping to determine whether the cold spot is a curious imperfection or a profound clue to the hidden nature of reality. And as we ponder this enigmatic feature, let us take another step further into the depths of the unknown, turning our attention to the chaotic, fluctuating realm of the smallest scales, quantum fluctuations, and the mysterious concept of cosmic foam. Now turning to the next challenge in our cosmic journey, we descend from the vast expanses of the universe to its tiniest, most bewildering realm, quantum fluctuations and the concept of cosmic foam. Imagine space-time not as a calm, continuous fabric, but as a seething, frothing sea of activity on scales so small they defy everyday comprehension. This idea of cosmic foam, introduced by physicist John Wheeler, suggests that at the smallest possible scales, far beyond what telescopes or particle accelerators can currently probe, space-time itself is in constant motion, bubbling with unpredictable fluctuations. These tiny, fleeting distortions arise from the inherent uncertainty of quantum mechanics, where even empty space is never truly empty. Instead, particles and antiparticles blink into and out of existence in an endless dance, borrowing energy from the vacuum only to vanish again almost instantly. But what makes quantum foam so tantalizing is its potential to reshape how we understand the very nature of reality. These fluctuations, seemingly chaotic and random, are thought to play a crucial role in the formation of the universe as we know it. For instance, during the moment of cosmic inflation, these quantum instabilities may have been stretched to cosmic proportions, seeding the galaxies, stars, and structures we see today. In essence, the largest cosmic structures owe their existence to the tiniest quantum events, linking the incomprehensibly small to the unimaginably vast in a way that highlights the interconnectedness of the universe. Yet, despite its importance, quantum foam remains one of the least understood aspects of modern physics. Theorists struggle to reconcile its implications with our current understanding of gravity and space-time. Our best description of gravity, Albert Einstein's theory of general relativity, treats space-time as smooth and continuous, but the wild fluctuations of quantum foam introduce a level of chaos that general relativity cannot easily account for. This inability to merge quantum theory with gravity represents one of the greatest challenges in theoretical physics, motivating efforts to develop a unified framework, often referred to as a theory of everything. Adding to the mystery, some suggest that studying quantum foam in greater detail could unlock answers to questions about black holes, the Big Bang, and even the fundamental structure of the universe itself. Could it hold the secret to the origins of space and time? Could it illuminate hidden dimensions or provide clues to how gravity actually works on the smallest scales? These questions drive scientists to push the boundaries of experimentation and theory, even as the true nature of quantum foam remains shrouded in uncertainty. What is perhaps most captivating about quantum foam is its paradoxical nature. Its influence is everywhere, subtly shaping the universe, yet it remains almost impossible to observe directly. To glimpse this chaotic sea of activity would require technological leaps far beyond our current capabilities, forcing us to rely instead on mathematical models, indirect evidence, and a dose of imagination to piece together its mysteries. As we ponder the implications of quantum foam, it serves as a humbling reminder of how much we have yet to discover about the universe's most fundamental layers. And with that, let us take a bold leap from the microscopic to a profoundly larger and equally puzzling idea, the possibility that our universe is merely one of many, as we dive into the tantalizing concept of the multiverse. With the next phase of the journey in sight, we delve into one of the most provocative and mind-bending ideas in modern science, the multiverse. Imagine for a moment that the universe we inhabit, filled with billions of galaxies, stars, planets, and all of human existence, is not the entirety of reality but just one among countless others. This is the essence of the multiverse concept, a notion that suggests there could be an infinite number of universes beyond our own, each with its own unique laws of physics, dimensions, and perhaps even versions of you and me. At the heart of this idea lies string theory, a framework that seeks to unify all the forces of nature by describing fundamental particles not as points but as tiny vibrating strings. According to some interpretations of string theory, our universe may be one of many bubbles floating in an enormous cosmic sea of possibilities. These bubbles could form, collide, or even spawn new universes in a process that may occur endlessly. In this view, the Big Bang that gave birth to our universe might not be a unique event but rather one of countless similar occurrences across an unthinkably vast multiverse. The multiverse concept also finds support in the peculiar phenomenon of cosmic inflation, the rapid expansion that occurred in the first fractions of a second after the Big Bang. Some theories propose that inflation never truly stopped but continues in regions beyond our observable universe, creating an infinite patchwork of universes, each with its own distinct properties. This idea, often referred to as eternal inflation, raises the possibility that our universe is just one small piece of a much larger and infinitely diverse puzzle. But while the multiverse may offer a dazzling explanation for some of the mysteries that puzzle scientists, such as why the constants of nature seem perfectly fine-tuned for life, it also raises profound and unsettling philosophical questions. If there are infinite universes, does that mean every possible version of reality exists somewhere? Are there versions of us making different choices, living different lives, or existing in entirely unrecognizable forms? And if our universe is one of many, what does that say about our place in existence? Are we merely one small, random strand in an infinite cosmic tapestry? Or is there a deeper significance to our particular universe being the way it is? Despite its allure, the multiverse remains a deeply contentious topic. Critics argue that it strays dangerously close to the realm of philosophy or even science fiction, as it is incredibly difficult, if not outright impossible, to test or observe directly. Without tangible evidence, some scientists question whether the multiverse is a legitimate scientific theory or simply a speculative idea that stretches the boundaries of what can be known. Others, however, suggest that indirect evidence such as patterns in the cosmic microwave background or the fine-tuning of physical constants could one day lend credibility to the multiverse concept. What captivates both supporters and skeptics alike is the sheer scale of possibility the multiverse represents. If true, it would radically redefine our understanding of reality, challenging deeply held assumptions about uniqueness, causality, and the very nature of existence itself. The multiverse invites us to think beyond the confines of our observable universe, to consider the vast, often unfathomable scope of what might lie beyond. As we step back from this dizzying exploration, let us now turn to a different paradox that forces us to confront the limits of our knowledge, the enigmatic clash between quantum mechanics and gravity, encapsulated in the baffling mystery of the black hole information paradox. Now turning to the enigmatic confrontation at the heart of modern physics, we delve into the black hole information paradox. Imagine a scenario where information, the very essence of matter and energy, seemingly disappears without a trace. This is the profound puzzle posed by black holes, those celestial objects with gravitational forces so intense that nothing, not even light, can escape their grasp. According to classical physics, anything that crosses a black hole's event horizon, the boundary beyond which escape is impossible, is lost forever. Yet, quantum mechanics, the branch of physics governing the smallest scales, dictates that information cannot be destroyed. This apparent contradiction lies at the core of the black hole information paradox. The paradox emerges when we consider what happens to the information about the particles that fall into a black hole. Is it permanently erased, violating the fundamental principles of quantum mechanics, or is it preserved in some way we have yet to understand? When a black hole eventually evaporates over time through a process known as Hawking radiation, named after the renowned physicist Stephen Hawking, where does the information go? Hawking radiation suggests that black holes lose mass and energy gradually until they ultimately vanish, leaving us with the unsettling question: does the information about everything that fell into the black hole simply disappear with it? This would represent a direct conflict between quantum mechanics and general relativity, the theory that describes the large-scale structure of the universe. Scientists have proposed various theories to resolve the paradox. One idea is that information might be encoded in subtle changes to the Hawking radiation itself, effectively allowing it to escape the black hole in a highly scrambled form. Another concept suggests that information could be preserved on the event horizon in a two-dimensional, holographic way, a notion linked to the holographic principle, which posits that the three-dimensional universe might fundamentally encode its information on a two-dimensional surface. A more speculative idea is that black holes could serve as gateways to alternate regions of the universe or even other universes, where the information continues to exist in some form. This paradox is more than an abstract theoretical problem. It challenges our deepest understanding of the universe. Resolving it could bridge the divide between quantum mechanics, which excels at explaining the smallest scales, and general relativity, which governs the grand cosmic scales. Such a unification, often referred to as quantum gravity, remains one of the ultimate goals of modern physics. Yet, the black hole information paradox reminds us of how much we still do not know. It forces us to confront the strange and unexpected ways the universe works, urging us to push the boundaries of science in pursuit of answers. As the sun rises on the next chapter of our cosmic journey, we shift our gaze to another mystery that deepens our sense of wonder: the staggering energy and enigmatic light of quasars. As the next challenge unfolds, we venture into the realm of alien megastructures, gigantic theoretical constructs that could showcase the pinnacle of advanced extraterrestrial engineering. Beyond the concept of Dyson spheres, which are hypothesized to be colossal structures enveloping stars to capture their energy, lies an even wider array of imaginative possibilities. Consider the idea of a ring world, a massive, ring-shaped habitat that orbits a star, providing an almost infinite surface area for civilization to thrive. Such structures, popularized in science fiction, could theoretically support entire planetary ecosystems, harnessing stellar energy with remarkable efficiency. Then there is the concept of Alderson disks, unfathomably large disk-like structures surrounding stars, where life could exist on both sides of the disk. These ideas stretch the limits of what we can imagine as achievable engineering feats, suggesting levels of technological advancement far beyond our current capabilities. If extraterrestrial civilizations were capable of constructing such monumental megastructures, why have we yet to detect any definitive signs of their existence? One possibility is that these civilizations might deliberately cloak their activities, avoiding detection by radiating energy in ways that blend seamlessly with natural cosmic phenomena. Another theory proposes that technological civilizations inevitably meet a great filter, a hypothetical barrier that prevents them from reaching such advanced stages of development. Alternatively, it is possible that these megastructures do exist but are located in regions of the universe far beyond the reach of our most powerful telescopes. Even if these constructs emit detectable energy signatures, such as infrared radiation from waste heat, we may lack the sensitivity or focus to identify them amidst the vast backdrop of the cosmos. The search for alien megastructures is more than just a pursuit of advanced engineering. It is a quest to understand whether we are alone in the universe. It challenges our assumptions about technology, civilization, and even survival. Each unexplained signal and every uncharted star system fuels the tantalizing hope that one day we might uncover evidence of these grand cosmic designs. Until then, the mystery remains, spurring us to look deeper and dream bigger as we aim our gaze toward the unknown. Moving forward, we turn our attention to the unexplained bursts of energy from the depths of space, known as fast radio bursts, a phenomenon as fleeting as it is mysterious. Now turning to the origins of water on Earth, we delve into one of the most profound mysteries of our planet's history. Water, the lifeblood of all known forms of life, covers over 70% of Earth's surface, yet scientists still cannot definitively explain how it got here. One prominent theory suggests that water was delivered by icy comets or asteroids during the chaotic early stages of the solar system. These celestial bodies, rich in volatile compounds, may have bombarded the young Earth, releasing vast quantities of water upon impact. However, the isotopic composition of water in some comets does not always match Earth's water, raising further questions about whether they could truly be the primary source. Another possibility is that water may have formed directly within the Earth itself. Some researchers propose that chemical reactions between hydrogen and oxygen deep within the planet's mantle could have produced water, which then rose to the surface through volcanic activity. This theory, while intriguing, struggles to explain the sheer abundance of water on Earth compared to other terrestrial planets. A third hypothesis suggests a combination of both internal and external sources, with impacts from asteroids and comets complementing water that was already present on Earth or trapped within minerals during its formation. Adding to the complexity, scientists remain puzzled about why Earth has retained its water while neighboring planets like Mars and Venus have lost most of theirs. Was it Earth's magnetic field, its size, or its position in the so-called habitable zone that gave it this unique advantage? Perhaps it was a combination of all these factors, working together in a delicate balance that allowed water to persist in its liquid state. No single explanation has yet emerged as definitive, and the question of Earth's water origin remains one of the most tantalizing open issues in planetary science. Understanding where our water came from is not just a matter of unraveling Earth's past, it is also crucial for identifying habitable worlds elsewhere in the universe. If water is more common than we previously thought, it could dramatically increase the chances of finding life beyond our planet. As this enigma continues to inspire research and debate, it serves as a powerful reminder of how much there is still to learn about the interconnected forces that shaped Earth as we know it. With the next phase of the journey in sight, we now shift to another mystery that roams the cosmos, the rogue planets wandering the galaxy without a star to call home. Moving forward, we encounter the enigmatic phenomenon of rogue planets, celestial wanderers adrift in the vastness of interstellar space with no parent star to anchor them. These free-floating planets defy the conventional understanding of planetary systems, where planets typically form and remain within the gravitational grasp of a star. But rogue planets break this mold, instead roaming the galaxy untethered and mysterious. Their origins are a source of ongoing intrigue among scientists. One leading theory suggests that these planets may have formed within traditional star systems, only to be violently ejected due to gravitational interactions with other massive objects. Another possibility is that rogue planets might have formed in isolation, directly within pockets of gas and dust across the galaxy, bypassing the need for a central star altogether. What makes these solitary worlds even more fascinating is how they endure the cold and dark of space without the warmth of a nearby star. Rogue planets do not rely on stellar energy for heat, but some may retain internal warmth generated during their formation, thanks to radioactive decay or gravitational contraction. Additionally, some may harbor thick atmospheres or layers of ice that insulate and preserve potential heat sources deep within. This leads to the tantalizing possibility that, under certain conditions, rogue planets could support subsurface oceans, creating environments where life might exist even in the absence of sunlight. Detecting these wandering planets is no small feat. Without a star illuminating them, they are often invisible to traditional telescopes. Instead, astronomers use indirect methods such as gravitational microlensing, where the gravity of a rogue planet bends and magnifies light from a distant star as it passes in front of it. While this technique has revealed the existence of rogue planets, it also underscores how little we truly know about them. Are they rare anomalies, or could they be more common than planets within star systems? Some studies suggest there could be billions of these dark, drifting worlds in our galaxy alone, hinting at an unseen population that vastly outnumbers the planets we have identified so far. The existence of rogue planets challenges how we think about planetary formation and survival, while raising profound questions about the potential for life in the most unexpected corners of the cosmos. These enigmatic wanderers remind us that the universe often defies expectations, leaving us to ponder what other secrets might lie hidden in its uncharted depths. As our exploration continues, we turn now to a strange visitor from beyond our solar system, an interstellar object that has left scientists both puzzled and intrigued. Now turning to the peculiar case of Oumuamua, an interstellar object that streaked through our solar system in late 2017, leaving scientists awestruck and perplexed. Unlike anything previously observed, Oumuamua's elongated, cigar-like shape and rapid velocity immediately set it apart from typical comets or asteroids originating within our solar system. Its trajectory made it clear that Oumuamua hailed from a distant star system, making it the first known visitor of its kind to pass through. But the mysteries surrounding this object run much deeper than its place of origin. One of the most puzzling aspects of Oumuamua is its shape, long and thin, resembling a cosmic needle. This highly unusual configuration fueled debates about how it could have formed naturally. To add to the intrigue, Oumuamua displayed no visible tail or outgassing, the hallmark signs of a comet, despite passing close to the Sun. Instead, it appeared to accelerate slightly as it moved away from the Sun, a behavior that generally aligns with comets releasing gas or material. However, in this case, no such emissions were detected, leaving scientists scratching their heads over what could be causing this unexplained motion. Naturally, these anomalies sparked a wave of speculation about Oumuamua's true nature. While most theories suggest it is a natural object, some researchers boldly propose the possibility of it being an artificial construct, perhaps even a probe sent by an advanced extraterrestrial civilization. This idea gained traction due to Oumuamua's peculiar shape and the inexplicable forces acting upon it, though it remains a controversial hypothesis. Other theories include the idea that it could be a fragment of a larger body torn apart by gravitational forces, or even a type of interstellar iceberg composed of frozen hydrogen or nitrogen, which could explain its lack of visible emissions. Despite its brief visit, Oumuamua has left an enduring scientific legacy. Its discovery has sparked efforts to improve our detection and study of interstellar objects, ensuring that future visitors won't catch us unprepared. As for Oumuamua itself, it has long since disappeared into the darkness of space, taking its secrets with it. Could it represent a common class of interstellar travelers, or is it a once-in-a-lifetime anomaly? Only time and more observations will tell. And with that, we move from the mystery of a single interstellar visitor to the captivating phenomenon of time behaving strangely in the presence of black holes, a topic that challenges our understanding of reality itself. As the next challenge unfolds, we delve into the mind-bending phenomenon of time dilation near black holes, an occurrence that defies our everyday understanding of time itself. According to Einstein's theory of general relativity, massive objects like black holes warp the very fabric of space and time around them. This distortion leads to an extraordinary effect. Time slows down as you get closer to the immense gravitational pull of a black hole. To an outside observer, a clock near the event horizon of a black hole, the boundary beyond which nothing can escape, not even light, would appear to tick more slowly than one farther away. In fact, if an astronaut were hypothetically orbiting a black hole while their twin remained on Earth, the twin on Earth would age significantly faster. This stark difference in the passage of time is one of the many ways black holes challenge our perception of reality. What makes this even more fascinating is how this phenomenon connects to the broader implications of general relativity. Einstein's equations demonstrate that time and space are intertwined in a single continuum, meaning the presence of a black hole not only stretches space but also bends time. Near a black hole, this bending becomes extreme, resulting in what scientists term gravitational time dilation. The closer you are to the event horizon, the slower time moves relative to the rest of the universe. In theory, someone crossing the event horizon would experience time at an almost imperceptible pace compared to an observer far away, although they themselves might not feel anything unusual. This has profound implications for our understanding of the universe. Black holes essentially allow us to glimpse the strange relationship between gravity and time, providing real-life scenarios where Einstein's theories are tested and confirmed. They illustrate how time is not a fixed, universal constant as we once believed, but a fluid dimension influenced by mass and gravity. Interestingly, this phenomenon has practical applications closer to home as well. Satellites and global positioning system devices must account for time dilation caused by Earth's gravity to ensure accurate navigation. Despite everything we know, many questions still remain. What happens to time and indeed to matter inside a black hole? Does time stop altogether at the singularity, the infinitely dense core of a black hole? These enigmatic questions drive the cutting-edge research of physicists today. Black holes not only stretch our understanding of time, but also remind us of how much more we have yet to comprehend about the universe. And now, as we leave the cosmic mysteries of time behind, let us turn to a striking paradox that questions the very consistency of the universe's expansion rate, an enigma known as the Hubble tension. Moving forward, we encounter a perplexing enigma in cosmology, an unresolved conflict in measuring the universe's expansion rate, known as the Hubble tension. The Hubble constant, which represents how fast the universe is expanding, is a cornerstone of modern astrophysics. However, scientists face a puzzling challenge. Different methods of calculating this rate yield conflicting results. When astronomers use the cosmic microwave background, the faint glow left over from the Big Bang, they get one value for the Hubble constant. On the other hand, measurements based on observing the distances and velocities of nearby stars and galaxies give a noticeably different value. Both methods are precise within their own contexts, yet their results stubbornly disagree, leaving researchers questioning whether our understanding of the universe is incomplete. What makes this tension so intriguing is that it could point to new physics beyond our current theories. Some scientists propose that unknown forces or particles, possibly linked to dark energy or dark matter, might be influencing these measurements. Others suggest that perhaps our models of the early universe, or even the very geometry of space-time, need a fundamental rethink. This disparity forces us to confront whether there are unseen variables at play, ones that have evaded our detection but could reshape our understanding of cosmic evolution. The stakes are enormous. Resolving the Hubble tension could illuminate unknown aspects of the universe's past and future, providing critical insights into its ultimate fate. It might even reveal groundbreaking clues about the mysterious forces driving cosmic expansion. As researchers continue to refine their techniques and develop new approaches, this paradox serves as a reminder of how much there is still to learn about the universe we inhabit. And now, as we examine the Hubble tension's implications, let us shift our focus to the blazing mysteries of the universe's most luminous phenomena, quasars. Now turning to quasars, these cosmic powerhouses are among the most luminous and enigmatic phenomena in the universe. Quasars serve as the dazzling cores of distant galaxies, driven by the immense energy emitted as matter spirals into supermassive black holes. These black holes, millions to billions of times more massive than the Sun, exert such a tremendous pull that as surrounding gas and dust fall toward them, they form an accretion disk, a swirling, superheated region of matter. The intense friction and gravitational forces within this disk produce extraordinary amounts of light and radiation, making quasars visible across vast cosmic distances. What makes them even more remarkable is their incredible brightness. Some quasars shine so intensely that they outshine all the other stars in their host galaxies combined. This astonishing luminosity allows astronomers to use quasars as cosmic lighthouses, studying them to glean insights into the early universe. Their light, traveling billions of years, carries with it a history of cosmic evolution, revealing clues about the formation of galaxies and the large-scale structure of the cosmos. However, quasars remain shrouded in mystery. For instance, how do these supermassive black holes, the engines of quasars, grow to such enormous sizes? Are they born massive, or do they grow gradually by consuming surrounding matter over billions of years? Furthermore, while we understand that quasars are often found in young, active galaxies, we still do not fully grasp why some galaxies possess these hyperactive cores while others do not. Could their presence depend on unique galactic conditions or specific cosmic events that ignite this intense activity? Adding to the intrigue, the variability of quasars in brightness is another puzzle. They can exhibit dramatic fluctuations in their emissions over relatively short periods, sometimes just days or weeks. Such changes suggest rapid, dynamic processes occurring near the event horizons of their black holes, but the exact mechanisms remain uncertain. Moreover, some quasars emit powerful jets of particles that travel at nearly the speed of light, stretching across millions of light years. What regulates the formation and direction of these jets, and why do some quasars have them while others do not? Quasars also challenge our understanding of the universe's extremes. Their sheer distance from us means that most quasars we observe today existed billions of years ago, providing a glimpse into the universe's infancy. Yet this raises the question of why we see so few quasars in the nearby, more mature universe. Did the conditions that favored their formation cease to exist, or did they evolve into something else entirely? As researchers continue to unlock the secrets of quasars, these luminous beacons remind us of how much there is yet to discover about the cosmos' most energetic phenomena. And with this exploration of quasars complete, let us journey to the very boundary of the observable universe, where tantalizing questions await about what lies beyond. With the next phase of the journey in sight, we venture to the very edge of the observable universe, a boundary that marks the farthest reaches of what we can see. This limit is not determined by the physical edge of the cosmos, but rather by the distance that light has traveled since the universe began around 13.8 billion years ago. Beyond this horizon lies a realm that remains hidden, where light has not yet had enough time to reach us. But what secrets could this unobserved expanse hold, and how might it reshape our understanding of existence? The observable universe is a cosmic bubble, a vast sphere centered around Earth, stretching roughly 93 billion light-years in diameter. Within this bubble, we see billions of galaxies, each containing millions or even billions of stars, along with countless planets, nebulae, and other wonders. Yet beyond this boundary lies the unobservable universe, a region potentially teeming with untold mysteries. Could there be more galaxies and clusters arranged in patterns beyond our comprehension? Or perhaps entirely new laws of physics might govern these unseen realms, rewriting what we thought we knew about the cosmos. One of the most tantalizing questions is whether the universe beyond our observational limit continues indefinitely, or if it has a definitive shape and structure. Is it infinite, stretching endlessly in all directions, or is it finite but unbounded, looping back onto itself like the surface of a sphere? If the universe is infinite, then the possibilities are staggering. There could be countless planets, stars, and perhaps even versions of ourselves existing in a mirror-like cosmic repetition. But the mystery does not end there. Scientists speculate that what lies beyond this limit might even include phenomena that challenge our fundamental understanding of reality. For example, the multiverse hypothesis suggests that our universe could be just one of many, with entirely separate regions of space-time governed by their own physical laws. This raises profound questions about the very nature of existence and whether our observable universe is just a tiny fragment of a far larger, more complex whole. Another fascinating possibility involves the large-scale structure of the cosmos itself. The distribution of galaxies within the observable universe reveals a pattern resembling a cosmic web, with vast voids separating clusters and filaments of galaxies. Could this pattern extend endlessly, or might there be variations or disruptions beyond the horizon? Some theories even hint at the existence of megastructures or intergalactic phenomena so vast and alien that they defy our imagination. And as we gaze toward this ultimate boundary, we face the question of time itself. Because the light from the edge of the observable universe has traveled for billions of years to reach us, we are essentially looking back in time, seeing the universe as it was in its infancy. This profound reality opens the possibility that the regions we cannot yet observe may hold clues to the very origins of existence, from the birth of stars and galaxies to the formation of the first elements. Yet, despite all our efforts, the edge of the observable universe remains both a limit and a challenge, a line that defines how much we can currently know. The horizon reminds us that there is so much more to uncover, so many questions left unanswered. And as we ponder the mysteries of this boundary, it leads us to an even larger question. What governs the universe's vast cosmic structure, the intricate web that connects galaxies and shapes the universe at its grandest scale? Now turning to the intricate design of the cosmic web, this immense structure is one of the most breathtaking and perplexing features of the universe. Imagine a vast network where galaxies and clusters are interconnected by filaments of dark matter and gas, forming a web-like pattern that stretches across the cosmos. These filaments are not just random alignments, but are believed to be the scaffolding upon which the universe is built, guiding the distribution of galaxies and shaping the grand architecture of space itself. Between these filaments lie enormous voids, regions almost entirely devoid of matter, creating a stark contrast that highlights the web's intricate design. But how did this cosmic web come to be? Scientists believe its origins trace back to the very early universe, mere moments after the Big Bang, when tiny quantum fluctuations in the dense, hot plasma laid the groundwork for the large-scale structures we observe today. Over billions of years, gravity acted on these initial ripples, amplifying them into vast filaments, nodes, and voids. This process was further influenced by the enigmatic forces of dark matter and dark energy, which continue to affect how the web evolves. Yet, the exact mechanics behind this formation remain a mystery, with many questions still unanswered. For instance, what precisely dictates the shape and scale of the web? Why are some regions densely packed with galaxies while others are almost entirely empty? Could the distribution of matter within the web be connected to unknown forces or even alternate dimensions? These inquiries stretch the limits of our understanding, hinting at deeper, more fundamental laws of physics that govern the universe at its largest scales. And the cosmic web is not just a static structure, its evolution is ongoing. As galaxies merge and interact along the filaments, they contribute to the web's dynamic nature, creating a constantly shifting tapestry of celestial activity. This interaction also raises questions about the role of dark matter, which is theorized to form the backbone of the web, and dark energy, which drives the universe's expansion and may subtly reshape the web over time. Furthermore, the cosmic web is pivotal in influencing the conditions for galaxy formation. Scientists have discovered that galaxies located within the filaments tend to develop differently from those in more isolated areas, suggesting that the web's structure directly affects the life cycle and behavior of galaxies. This finding not only deepens the mystery but also provides a window into understanding how the universe's large-scale environment impacts its smaller components. As we study the cosmic web, we are reminded of the delicate balance and complexity that underpins the universe. The web's sprawling filaments, vast voids, and intricate connections reveal a universe that is at once ordered and chaotic, a masterpiece shaped by forces we are only beginning to comprehend. And as we unravel its secrets, the cosmic web invites us to ponder the larger question: what roles do unseen forces play in weaving the fabric of existence, and what other mysteries might be hidden within these intergalactic threads? Moving forward, let us explore the strange and extreme world of extrasolar weather phenomena so bizarre they defy our earthly imagination. Picture a planet where it rains glass sideways, whipped around by winds that reach speeds of thousands of miles per hour. This is not science fiction, but the reality of some distant exoplanets. Take, for instance, a planet known as HD 189733b, a gas giant located around 63 light-years from Earth. Here, the atmosphere is so scorching that it can melt metals, and the rain consists of molten glass carried by relentless winds across the skies at blistering speeds. This is just one example of the extraordinary weather conditions scientists have observed beyond our solar system, shedding light on the diversity and extremities of alien worlds. But how do such extreme conditions come to exist? The answer begins with the unique characteristics of these planets and their environments. Many exoplanets, especially the so-called hot Jupiters, orbit perilously close to their parent stars. This proximity subjects them to intense radiation, which heats their atmospheres to temperatures of thousands of degrees. At these extreme levels of heat, ordinary materials like minerals and metals vaporize, forming strange chemical compositions in their skies. These bizarre atmospheric dynamics not only create surreal weather patterns, but also pose intriguing challenges for scientists as they try to understand the delicate balance of chemistry and physics at play. One of the most fascinating aspects of extrasolar weather is its potential to reveal secrets about planetary formation and evolution. For instance, the presence of certain elements in a planet's atmosphere can provide clues about its origins, such as whether it formed close to its star or migrated inward from a more distant orbit. Similarly, observing these alien climates helps scientists test their theories about atmospheric behavior under extreme conditions, offering a new perspective on how planets adapt to their environments. Then there are the ultra-hot gas giants, whose temperatures exceed those of some stars. These planets challenge traditional models of planetary physics. For example, their atmospheres can be stripped away by their parent stars, creating trails of gas in space and altering the planet's long-term evolution. Studying such dramatic processes allows scientists to refine their understanding of how planets interact with their host stars and what this interplay means for the broader system they inhabit. These discoveries also hold implications for the search for life beyond Earth. By studying the diverse weather patterns of exoplanets, researchers can better understand the range of conditions that might allow life to develop or inhibit its chances entirely. While planets with glass rain and scorching heat might seem inhospitable, they broaden our appreciation of the vast array of environments that exist in the cosmos, reminding us that the conditions for life as we know it may be rare, or that life itself might thrive in forms we cannot yet imagine. As we delve deeper into the mysteries of extrasolar weather, we are struck by how these alien worlds challenge and expand our understanding of the universe. The extreme climates, shaped by forces far more intense than those on Earth, are a testament to the incredible diversity of planetary systems. They remind us that the universe is a place of endless wonder, with each discovery opening the door to new questions about how planets are made, how they evolve, and what they might teach us about our own place in the cosmos. With the next phase of the journey in sight, we turn our gaze to yet another enigma, the missing baryons of the universe, and the quest to uncover this hidden matter. Now turning to the perplexing mystery of the missing baryons, we confront a conundrum that has puzzled astronomers for decades. Baryons, which are particles like protons and neutrons that make up the ordinary matter in stars, planets, and even people, are expected to account for about 5% of the universe. Yet when scientists tally up all the observable baryons in galaxies, stars, and gas clouds, they find that roughly half of them are missing. So, where is this elusive matter hiding? Recent research points toward vast stretches of intergalactic space as the likely hiding place for these missing baryons. These regions, known as the warm-hot intergalactic medium, are thought to consist of thin filaments of gas that stretch like a web between galaxies. This gas is incredibly diffuse, making it nearly impossible to detect with traditional instruments. However, scientists have developed innovative methods to track down this hidden matter. One breakthrough involves observing how light from distant quasars, which are extremely luminous objects powered by black holes, gets absorbed as it travels through these intergalactic filaments. These absorption patterns act like fingerprints, revealing the presence of the baryons hidden in the cosmic web. Another exciting method involves studying fast-moving particles called high-energy neutrinos. These particles interact with the baryonic matter in the intergalactic medium, providing indirect evidence of where the missing baryons are located. Advanced telescopes and space missions are also helping to map this elusive matter by capturing faint X-rays emitted by the hot gas in these regions. Slowly but surely, these efforts are painting a clearer picture of the universe's missing baryons. Uncovering these hidden particles is not just about solving a cosmic accounting problem. It has profound implications for our understanding of how galaxies form and evolve. The baryons in the intergalactic medium play a crucial role in fueling galaxies, providing the raw material for the creation of stars and planets. By piecing together the puzzle of the missing baryons, scientists are gaining valuable insights into the life cycle of galaxies and the large-scale structure of the universe. This mystery also raises broader questions about the interplay between visible and invisible forces in the cosmos. While dark matter and dark energy dominate the universe and remain enigmatic in their own right, the missing baryons remind us that even the ordinary matter we think we understand still holds surprises. Solving this puzzle requires cutting-edge technology and creative thinking, pushing the boundaries of what we know about the cosmos. As the search for the missing baryons continues, we are reminded of the boundless complexity and interconnectedness of the universe. Each discovery brings us closer to understanding how the cosmos operates on both grand and microscopic scales. With this mystery still unfolding, we now turn our focus to another intriguing question: the phenomenon of space roar and what it reveals about the unseen forces of the universe. Now turning to the enigma of space roar, we encounter a mystery that has baffled scientists since its discovery. Space roar refers to the surprisingly strong radio waves detected from the depths of the universe, far louder than anything scientists had anticipated. This phenomenon was first uncovered by a project aimed at studying faint signals from the earliest galaxies using a specialized instrument aboard a high-altitude balloon. Instead of the subtle whispers of the early universe, what they found was an overwhelming roar, 6 times stronger than all known sources of radio waves combined. So, what could possibly be causing this? One theory suggests that the source might be galaxies themselves, emitting far more radio waves than previously thought. However, this idea raises another question: why would galaxies in the distant universe produce such intense signals when closer ones do not? Another line of speculation involves vast clouds of gas in intergalactic space that could amplify radio waves through a process we do not yet understand. Some scientists have even pondered whether space raw might hint at phenomena not yet accounted for in our models of the universe. Adding to the intrigue, researchers have considered whether this mysterious signal could be tied to the cosmic microwave background radiation, the faint glow left over from the Big Bang that permeates the universe. Could there be an unknown interaction between this ancient radiation and other cosmic structures, creating the intense radio waves we now detect? There is even a fringe possibility that space raw might stem from an entirely exotic source, such as new forms of matter or energy that have eluded discovery. What makes space raw particularly puzzling is the sheer difficulty of pinpointing its origin. Unlike visible light, radio waves can be influenced by countless factors as they travel through space, from magnetic fields to interactions with particles. This makes tracing the source of the raw a daunting task for astronomers. Yet, the quest to unravel this mystery continues, with new experiments and advanced instruments designed to separate this enigmatic signal from the background noise of the cosmos. Understanding space raw could unlock new insights into the large-scale structure of the universe and the forces that shape it. It reminds us how little we truly know about the radio universe, a realm of cosmic phenomena that operates largely outside our visible spectrum. As scientists delve deeper, every clue brings us closer to uncovering what lies behind this cosmic roar, bridging yet another gap in our understanding of the cosmos. With the mystery of space raw lingering like a question mark in the vastness of space, we now shift our attention to a different yet equally fascinating puzzle: the peculiar structure at the center of our own galaxy, the galactic bar, and the secrets it holds about the Milky Way's evolution. Moving forward, we turn our gaze toward the heart of our galaxy to uncover the enigmatic structure known as the galactic bar. This elongated band of stars, gas, and dust stretches across the center of the Milky Way, serving as a cosmic bridge between its spiral arms. While it may appear as just another feature of our galaxy, the galactic bar holds profound mysteries that scientists have yet to unravel. One of the most pressing questions is what sustains this structure over billions of years. Why does it not dissipate or collapse under the immense gravitational forces at play? The galactic bar is believed to act as a kind of gravitational engine, funneling gas inward toward the supermassive black hole at the galaxy's core, while simultaneously driving material outward to form new stars along the spiral arms. But while this mechanism suggests the bar is incredibly dynamic, its long-term stability is puzzling. Computer simulations of galaxies often show bars forming naturally over time, but these models also indicate that such bars should eventually weaken. Yet the bar in the Milky Way appears remarkably persistent. Could there be hidden forces at work that we simply do not understand? One intriguing possibility is that dark matter, the unseen and mysterious substance that makes up a significant portion of the universe's mass, could play a stabilizing role. By exerting additional gravitational influence, dark matter might help maintain the bar's structure over cosmic timescales. Another theory posits that the bar's longevity could be linked to interactions with the Milky Way's surrounding environment, including its satellite galaxies and the halo of stars that envelop it. Could these influences be subtly reshaping and reinforcing the bar, keeping it from fading away? Adding another layer of complexity, the bar's rotation presents its own set of riddles. Observations suggest that the bar rotates at a speed that is neither too fast nor too slow, perfectly synchronized with the inner regions of the galaxy. What regulates this precise balance, and how does it impact the overall dynamics of the Milky Way? Scientists are also investigating the possibility that the bar has not always been as prominent as it is today. Some evidence hints that it may have grown stronger over billions of years, evolving along with the galaxy itself. Studying the galactic bar is not just about understanding our own galaxy. It holds key insights into the formation and evolution of barred spiral galaxies throughout the universe. By decoding the mysteries of this central feature, we not only learn about the forces shaping the Milky Way, but also uncover universal patterns that govern galaxies far beyond our own. As researchers continue to probe the nature of the galactic bar with increasingly sophisticated tools, they inch closer to solving one of the most fascinating puzzles in galactic astronomy. With the galactic bar revealing the interconnected dynamics of our galaxy, we now venture into an even smaller scale yet equally baffling enigma, the ghostly realm of high-energy neutrinos and the secrets they carry from the distant corners of the cosmos. With the next phase of the journey in sight, we delve into the elusive world of high-energy neutrinos, often referred to as ghost particles. These tiny, nearly massless particles are so enigmatic that they barely interact with anything in the universe, passing through entire planets, stars, and even galaxies as if they do not exist. Yet, some of these neutrinos carry unimaginably high energies, hinting at violent and mysterious origins beyond our galaxy. But what could possibly create such extraordinary particles, and why do they remain one of the most puzzling riddles in astrophysics? High-energy neutrinos are detected when they occasionally interact with matter, producing faint flashes of light deep in detectors buried under ice or water. These rare interactions allow scientists to track their origins, and what they have found is astonishing. Many of these neutrinos seem to come from locations far beyond the Milky Way, possibly linked to some of the most extreme and energetic events in the universe. Potential sources include supermassive black holes feasting on surrounding material, exploding stars known as supernova, and even gamma-ray bursts, which are considered the most powerful explosions in the cosmos. However, pinpointing their exact origins remains a significant challenge. One of the theories suggests that high-energy neutrinos might arise from interactions between cosmic rays, high-speed particles traveling through space, and interstellar matter or radiation. These collisions could generate neutrinos with extraordinary energy levels, but the specific sites where such interactions occur are difficult to identify. Despite extensive research, the sources of the most energetic neutrinos continue to elude scientists, leaving the question open. Are we missing a fundamental mechanism that produces these ghostly messengers? Adding to the mystery, neutrinos provide a unique advantage. They can travel vast distances across the universe without being absorbed or deflected by magnetic fields or cosmic dust. This makes them ideal carriers of information about distant and otherwise inaccessible regions of space. By studying high-energy neutrinos, astronomers hope to uncover details about extreme astrophysical phenomena that cannot be observed through traditional methods like light or radio waves. These particles might even hold clues about the most fundamental forces shaping the universe. Yet, their nearly undetectable nature makes them incredibly hard to study. Each high-energy neutrino that enters our detectors represents just the tiniest fraction of the countless neutrinos streaming through the Earth every second. This rarity complicates efforts to gather enough data to draw definitive conclusions. Still, researchers are building ever more sensitive instruments, like massive underwater detectors and arrays embedded deep in Antarctic ice, to catch these fleeting interactions. The study of high-energy neutrinos is not just about solving an astrophysical puzzle. It promises to open a whole new window into the cosmos. These ghost particles could reveal unknown processes and help us understand the most violent and energetic events in the universe. As scientists push the boundaries of technology and theory, the secrets carried by these ghostly messengers remain one of the most tantalizing mysteries of modern astronomy. With this haunting enigma in mind, we now shift our focus to yet another cosmic question. How do supermassive black holes, the colossal anchors of galaxies, come into existence? As the next challenge unfolds, we venture into the heart of galaxies to uncover the enigma of supermassive black holes. These colossal regions of space, so dense that not even light can escape their gravitational pull, are thought to act as the anchors of galaxies, influencing their formation and behavior. With masses millions to billions of times that of our Sun, supermassive black holes represent some of the most extreme objects in the cosmos. But how do these cosmic titans come into existence? Are they the result of smaller black holes merging and growing over time, or is their formation a process entirely different from what we currently understand? One prevailing theory suggests that supermassive black holes may begin as stellar black holes, those formed by the collapse of massive stars gradually accumulating mass by consuming nearby gas, dust, and even stars. Over billions of years, these smaller black holes might merge with others or absorb vast amounts of material, eventually reaching supermassive proportions. However, this process raises questions. Could galaxies in the early universe, home to supermassive black holes, have formed them so quickly through this gradual method, or does this suggest another, more rapid mechanism at play? Another intriguing possibility posits that supermassive black holes could have formed directly from gigantic clouds of gas collapsing under their own gravity in the early universe. Known as direct collapse black holes, these primordial giants could bypass the smaller, more incremental stages entirely, giving rise to supermassive black holes much earlier than other theories might predict. If true, this would mean that the seeds of these immense gravitational powerhouses were sown almost immediately after the birth of the universe. Yet another potential pathway could involve dense clusters of stars in the centers of young galaxies. These clusters might experience runaway collisions where individual stars combine to form an increasingly massive object, eventually collapsing into a supermassive black hole. This theory suggests that the intense gravitational interactions within such clusters could accelerate the growth process, offering another explanation for the appearance of supermassive black holes in the universe's infancy. Despite these fascinating theories, the exact origins of supermassive black holes remain one of astrophysics' most perplexing puzzles. Compounding the mystery is their sheer size and the rapid pace at which some of them seem to have formed, especially in the early universe when material for growth was thought to be scarcer. Evidently, supermassive black holes challenge our understanding of cosmic evolution and raise profound questions about the mechanisms that drive their growth. Adding to their mystique, supermassive black holes play a vital role in shaping their galaxies. Through a process called feedback, as they consume matter, they release powerful streams of energy that can regulate star formation and even influence the distribution of gas across the galaxy. Understanding how these giants form could, therefore, unlock deeper insights into galaxy formation and evolution as a whole. The search for answers continues as scientists use tools like advanced computer simulations and telescopes capable of peering into the distant past to study the earliest galaxies. Observatories equipped with advanced technology are helping researchers uncover black holes in various stages of their growth, shedding light on how these cosmic behemoths evolve over time. Yet for every answer uncovered, new questions emerge, keeping the mystery alive. Supermassive black holes are not just gravitational juggernauts but also cosmic storytellers. They carry the secrets of galaxies from their origins to their ultimate fate. While we may not yet know exactly how they are born, each new discovery brings us closer to unraveling their story. And from the heart of galaxies, we now turn our gaze outward to another celestial marvel, the mysteries surrounding the Moon's formation. Now turning to the mysteries of our celestial neighbor, the Moon, we find ourselves pondering a fundamental question. How did the Moon come to be? Despite being one of the most familiar objects in the night sky, the Moon's origin remains a topic of intense debate among scientists, with multiple theories vying for acceptance. The most widely discussed hypothesis is the giant impact theory. According to this idea, billions of years ago, a Mars-sized object collided with the early Earth, ejecting a massive amount of debris into space. Over time, this debris coalesced to form the Moon. While this theory explains several aspects of the Moon's composition and its proximity to Earth, it does not account for everything. For instance, why is the Moon's composition so similar to that of Earth's mantle, yet different enough to suggest the involvement of another celestial body? Another competing idea is the capture theory, which proposes that the Moon formed elsewhere in the solar system and was later captured by Earth's gravity. While intriguing, this scenario faces challenges in explaining how such a large object could have settled into a stable orbit without breaking apart or escaping Earth's gravitational pull. Then there is the co-formation theory, which suggests that the Moon and Earth formed simultaneously from the same primordial disk of gas and dust. However, this theory struggles to explain the Moon's distinct lack of iron compared to Earth's core, as well as other compositional differences between the two bodies. Adding to the complexity is the fission theory, an older idea that has seen occasional revival. It speculates that the Moon was once part of Earth and was flung into space due to the planet's rapid rotation or a massive event in its early history. Though this would explain some compositional similarities, it requires Earth to have been spinning at an implausibly high speed for this to occur. Each of these theories presents compelling arguments but leaves crucial questions unanswered. For instance, why does the Moon have less volatile material than Earth, suggesting it endured intense heat during its formation? And why is there evidence of water deep within the Moon, contrary to what some formation scenarios would predict? Recent studies have even uncovered unusual isotopic ratios in lunar samples, adding new layers of complexity to the mystery. These anomalies force scientists to rethink existing theories or consider that the Moon's formation may involve a combination of processes rather than a single event. Modern advancements such as lunar missions and laboratory analysis of moon rocks continue to provide tantalizing clues. Robotic explorers like those from recent missions are uncovering new data about the Moon's surface, its internal structure, and its geologic history. These findings help refine our models and bring us closer to piecing together the Moon's enigmatic story. Despite decades of research, the Moon's origin remains elusive, a reminder that even our closest celestial companion holds secrets we have yet to fully uncover. But as we search for answers about the Moon's past, we are also reminded of its profound influence on Earth, from stabilizing our planet's axis to shaping the tides that govern life. It serves as a constant reminder of the interconnectedness of all things in the cosmos. And with these thoughts, we set our sights on another cosmic enigma, the puzzling nature of interstellar clouds. As the next chapter unfolds, we venture into the vast expanse between stars to unravel the mysteries of interstellar clouds, enormous regions of gas and dust that hold the secrets to the birth and evolution of the cosmos. These clouds, often stretching for hundreds of light years, are not merely empty voids but rather the cradles where stars and planets are born. Two of the most fascinating examples are the local bubble and the Oort cloud, each offering a glimpse into the complex processes that shape solar systems and galaxies. The local bubble is a frothy region of low-density gas surrounding our solar system, thought to have been carved out by multiple supernova explosions millions of years ago. Imagine colossal stellar explosions scattering material across space, creating a hot, tenuous cavity in the interstellar medium. This bubble provides a unique perspective on the violent events that occur in our galaxy's history and how they influence the environment around us. Its boundaries, where the tenuous gas meets denser regions, are areas of active study, as they may hold insights into the interplay between supernova-driven shockwaves and the formation of new stars. On the other hand, the Oort cloud represents an entirely different type of interstellar mystery. Surrounding our solar system like a distant shell, this theoretical cloud is thought to be a vast reservoir of icy objects, remnants from the early days of planetary formation. It is believed to extend nearly halfway to the nearest star, making it one of the most remote and enigmatic structures tied to our solar system. The Oort cloud is also suggested to be the source of most long-period comets' icy wanderers that occasionally make their way toward the Sun, offering us a fleeting look at the building blocks of the early solar system. Yet, despite its theoretical significance, no direct evidence of the Oort cloud has been found, leaving its existence as one of astronomy's enduring puzzles. Both the local bubble and the Oort cloud highlight how interstellar clouds contribute to the life cycle of the cosmos. They serve as repositories of material, fuel for star formation, and even as time capsules of the galaxy's past. These clouds also play a vital role in recycling elements forged in stars, redistributing them across the galaxy to form new generations of solar systems. Without these processes, the universe as we know it would look vastly different, yet many questions remain. How exactly do the complex interactions within these clouds lead to the formation of stars and planets? What triggers the collapse of these diffuse regions of gas and dust into dense pockets where gravity takes over? And what role do interstellar magnetic fields and cosmic radiation play in shaping these structures? The answers to these questions are critical to understanding not just the history of our own solar system, but the mechanisms that govern galaxies as a whole. Advances in technology, from infrared telescopes to radio arrays, are allowing astronomers to peer deeper into these mysterious regions. Observations of nearby molecular clouds, like the famous Orion Nebula, are revealing the detailed processes that transform interstellar clouds into stellar nurseries. Meanwhile, the study of high-velocity gas streams and cosmic dust grains offers clues about how material from these clouds interacts with existing galactic structures. Interstellar clouds remain a testament to the dynamic, ever-changing nature of the cosmos. They challenge us to piece together the story of how galaxies evolve and to understand the intricate web of forces that shape the universe. As we continue our journey through the mysteries of space, let us now turn our attention to a phenomenon equally puzzling and electrifying: the theoretical concept of white holes. As the next phase of our cosmic exploration unfolds, we delve into the enigmatic concept of white holes. Theoretically, white holes are the polar opposites of black holes. While black holes are infamous for their immense gravitational pull, which traps everything including light, white holes are proposed to do the exact reverse. They repel matter and energy, forbidding anything from entering their boundaries. Imagine a region in space where, instead of pulling everything inward, forces push everything outward. This idea is as perplexing as it is fascinating, challenging our fundamental understanding of physics and the universe. White holes first emerged as a solution in Einstein's equations of general relativity, appearing as a mathematical counterpart to black holes. According to these equations, if black holes exist, then white holes could theoretically exist as well. But their potential existence raises profound questions. For instance, could white holes be linked to black holes through hypothetical structures like wormholes, creating pathways to different regions of space-time? Or are they purely mathematical constructs with no basis in reality? Despite their theoretical allure, no evidence of white holes has been observed in the universe. Scientists search for telltale signs, such as bursts of energy or unusual particle movements that could signal the presence of a white hole, but so far these remain elusive. Some theories even suggest that white holes might have existed only in the early moments after the universe's creation, playing a critical role in shaping the cosmos as we see it today. The white hole hypothesis also sparks questions about the very nature of space-time. Could they offer insights into what happens when the laws of physics are pushed to their limits? Or might they provide clues about the interplay between quantum mechanics and the fabric of the cosmos? Researchers continue to explore these possibilities, using advanced simulations and mathematical models to test the boundaries of our understanding. As we ponder the theoretical existence of white holes, we also confront the broader mystery of whether our universe holds phenomena so strange that they defy even the most advanced scientific theories. With these questions in mind, let us now shift our focus to another subject that keeps astronomers up at night: the anisotropy of the universe and the peculiar asymmetries that hint at hidden cosmic secrets. Now turning to the anisotropy of the universe, we encounter a fascinating puzzle etched into the very fabric of the cosmos. At first glance, the universe appears remarkably uniform, with galaxies, stars, and cosmic structures scattered evenly across the vast expanse of space. However, on closer inspection, scientists have discovered subtle irregularities in this seeming uniformity, especially in the temperature of the cosmic microwave background radiation. This radiation, often referred to as the afterglow of the Big Bang, provides a snapshot of the universe when it was just 380,000 years old. Yet, instead of being perfectly smooth, it reveals tiny temperature fluctuations, regions slightly warmer or cooler than their surroundings. These variations, known as anisotropies, have intrigued scientists for decades, as they hold clues to the universe's earliest moments and its vast-scale structure today. One of the leading theories suggests that these anisotropies originated from quantum fluctuations in the primordial universe. As the cosmos expanded at an exponential rate during what scientists call the period of cosmic inflation, these tiny quantum fluctuations were stretched out, eventually seeding the formation of galaxies and galaxy clusters. In this sense, the anisotropies in the cosmic microwave background act like fingerprints left behind by the universe's infancy, providing a glimpse into the physics of those formative moments. However, the story grows even more mysterious when researchers examine certain peculiarities within these temperature fluctuations. For example, there's the infamous cold spot, a region that is significantly cooler than other parts of the cosmic microwave background. Some scientists argue that it could be a statistical anomaly, while others propose more exotic explanations, such as a collision with another universe or the presence of a massive cosmic void in that direction. These theories, though speculative, challenge us to consider possibilities far beyond our current understanding of cosmology. The anisotropy of the universe also raises profound questions about its overall shape and nature. Could these irregularities hint at a universe that is not entirely uniform but shaped by some unknown forces or hidden dimensions? Or do they point to limitations in our observational tools and theories, showing us the boundaries of what we can currently know? As scientists continue to analyze these temperature maps with more precise instruments, such as those aboard space telescopes, we inch closer to unraveling the secrets of the cosmos. With this enigmatic interplay of temperature fluctuations and cosmic origins in mind, let us now set our sights on yet another mystery: the exact age of the universe and the complex debates surrounding whether it might be older than we currently estimate. As the next challenge unfolds, we dive into the ongoing debates about the age of the universe, a question that lies at the very heart of cosmic history. Current estimates suggest the universe is approximately 13,800,000,000 years old, a figure derived from meticulous measurements of the cosmic microwave background radiation, the movement of galaxies, and the oldest known stars. However, not all evidence aligns seamlessly with this timeline, sparking heated discussions among astronomers and physicists alike. One of the more puzzling findings comes from certain stars, known as metal-poor stars, that appear to be older than the universe itself according to current models. For example, the star designated as HD 140283, located in the Milky Way, has been calculated to be around 14 billion years old. This paradoxical result has left scientists questioning whether errors in measurement, unaccounted for physical processes, or gaps in our understanding of stellar evolution might be at play. In addition, recent advancements in technology have allowed for more precise observations of the rate at which the universe expands, a value referred to as the Hubble constant. Intriguingly, different methods of measuring this rate yield conflicting results. Some suggest a faster expansion rate, which would imply a younger universe, while others support a slower rate, potentially pointing to a much older universe. This growing tension, known as the Hubble tension, has left researchers grappling to reconcile these discrepancies and refine their models of cosmic history. If the universe is indeed older than currently calculated, it would force us to re-examine many foundational assumptions in cosmology. A revised timeline could reshape our understanding of the formation of galaxies, the evolution of stars, and the mechanisms that led to the universe as we observe it today. It might even suggest previously unknown processes at work during the earliest moments of existence. On the other hand, these debates underscore the limitations of our current observational tools and theoretical frameworks. They remind us that our view of the cosmos is far from complete, and that each new discovery has the potential to disrupt even our most established ideas. Whether the true age of the universe aligns with current estimates or turns out to be something vastly different, the pursuit of this knowledge reflects humanity's unyielding curiosity about our origins and place in the cosmos. Moving forward, we now turn our attention to another enduring cosmic enigma: the perplexing question of what drives high-energy cosmic rays and where they come from. Now turning to the enigmatic phenomenon of high-energy cosmic rays, we find ourselves confronted with a mystery that has baffled scientists for over a century. Cosmic rays are incredibly energetic particles, primarily protons, that streak through space and occasionally slam into Earth's atmosphere at astonishing speeds, some approaching the speed of light. What makes these particles so puzzling is not just their immense energy, but also their elusive origins. Scientists have long speculated about what could accelerate these particles to such extreme velocities. Possible sources include powerful events like supernova explosions, where the shock waves might act as cosmic particle accelerators, or the intense magnetic fields surrounding supermassive black holes at the centers of galaxies. Even more intriguing are ultra-high-energy cosmic rays, particles with energy levels so staggeringly high that they defy explanation. These rare cosmic wanderers, such as the one detected in 1991, nicknamed the "Oh my God" particle, carry as much energy as a fast-pitched baseball despite being smaller than an atom. Events capable of generating such energy are still a matter of intense debate. Some scientists propose gamma-ray bursts, which are among the most energetic explosions in the universe, while others suggest these rays could originate from regions near active galactic nuclei, massive jets of material ejected by supermassive black holes. Adding to the enigma is the fact that cosmic rays are notoriously difficult to trace back to their sources. Since they carry a charge, these particles are deflected by magnetic fields as they travel through space, making their paths completely unpredictable. This means even with advanced detection methods, pinpointing the origin of a single cosmic ray is akin to finding a needle in a haystack, especially on a cosmic scale. The mystery deepens further when considering the potential contribution of exotic phenomena, such as the annihilation of dark matter particles or collisions involving cosmic strings, theoretical one-dimensional defects in space-time predicted by some models of the universe. These possibilities push the boundaries of what we know, inviting us to consider entirely new physics that could reshape our understanding of energy and matter in the cosmos. Despite these challenges, progress is being made through cutting-edge observatories like the Pierre Auger Observatory in Argentina and the IceCube Neutrino Observatory in Antarctica. By studying the secondary particles produced when cosmic rays collide with Earth's atmosphere or ice, researchers are slowly piecing together clues about their sources and the processes that might generate them. Each discovery brings us closer to unraveling the secrets of these fascinating messengers from the farthest reaches of the cosmos. With the next phase of the journey in sight, we now turn our attention to the cosmic web, the grand, large-scale structure of the universe that connects galaxies in a stunning, interconnected pattern. As the next challenge unfolds, we arrive at the profound reflection often referred to as the pale blue dot conundrum, a term inspired by the iconic image captured by the Voyager 1 spacecraft in 1990. From a distance of over 3.5 billion miles away, Earth appears as nothing more than a tiny speck, a faint blue dot suspended in a vast cosmic abyss. This humbling perspective offers a striking reminder of our planet's fragility and the sheer enormity of the universe. Yet, beyond its poetic significance, the conundrum lies in the deep sense of mystery and curiosity it evokes about our place in the cosmos. Why does studying the universe invariably remind us of how little we truly comprehend? For one, the vastness of space stretches far beyond our ability to observe and measure, with billions of galaxies and countless stars lying beyond the reach of even our most advanced instruments. The more we learn, the more questions arise about the nature of life, the origins of the universe, and the fundamental laws that govern reality. Even the simplest questions, like why Earth harbors life while so many other worlds appear barren, remain shrouded in uncertainty. Moreover, the pale blue dot also challenges us to consider the limitations of human perception. We experience the universe through a narrow band of reality, what we can see, hear, and measure with the tools we have. Yet, phenomena like dark matter, dark energy, and quantum mechanics reveal that much of the universe operates outside the realm of our senses. In this way, every new discovery feels like peeling back a single layer of an infinitely complex puzzle, reminding us of the vast ocean of unknowns still waiting to be explored. This iconic image and the philosophical questions it raises also force us to confront a deeper truth: our interconnectedness with the universe. The atoms that make up our bodies were forged in the hearts of ancient stars, and every breath we take is tied to the planet's ability to sustain life. From that perspective, the pale blue dot becomes not just a symbol of our insignificance, but also of our shared responsibility to care for the only home we know. As we strive to understand the universe, we are continually reminded of the humility it demands. The pale blue dot serves as a mirror, reflecting both the limits of our knowledge and the boundless curiosity that drives us forward. And with that, we now shift our focus to the mysterious forces responsible for the continuous expansion of the universe, a phenomenon that further deepens our cosmic intrigue. Now turning to the expansion of the universe, we encounter one of the most profound and perplexing mysteries in modern cosmology. Imagine a reality where space itself, the very fabric of existence, is stretching, causing galaxies to drift farther apart from one another over time. This is not just a movement through space, but an expansion of space itself, a phenomenon first observed in the early 20th century when astronomers noted that the light from distant galaxies appeared to be redshifted, a sign that they were moving away from us. The discovery was revolutionary, leading to the understanding that the universe is not static but constantly growing. The question then arises: what is driving this cosmic expansion? For decades, scientists believed that gravity, the force pulling objects together, would eventually slow the universe's growth or even reverse it. But in the late 1990s, observations of distant supernova revealed something unexpected. The expansion of the universe is not slowing down but accelerating. This startling discovery led to the introduction of the term dark energy, a mysterious and invisible force that seems to be pushing the universe apart. Dark energy is thought to make up nearly 70% of the universe, yet its nature remains one of the greatest enigmas in science. Some propose it could be the cosmological constant, a term Albert Einstein included in his equations of general relativity, representing a kind of energy inherent to space itself. Others suggest it might be something entirely different, such as a dynamic field called quintessence that evolves over time. Yet, despite these theories, dark energy has so far eluded direct detection, leaving us to wonder whether it might point to physics beyond what we currently understand. Adding to the mystery are questions about the long-term implications of this expansion. If dark energy continues to dominate, the universe could face what scientists call the Big Freeze, where galaxies move so far apart that stars run out of fuel and the cosmos becomes dark and cold. Alternatively, if the nature of dark energy changes, it might lead to a big rip where the fabric of space stretches so violently that galaxies, stars, and even atoms are torn apart. The expansion of the universe not only challenges our understanding of physics, but also forces us to confront the limits of our knowledge. It reveals a reality where the largest structures in the cosmos are governed by forces we can barely begin to comprehend. As we explore these vast mysteries, we come to realize that understanding the universe may require not just new tools and experiments, but entirely new ways of thinking. And now, with this mind-bending concept in view, we turn our attention to the planet often called Earth's twin, but shrouded in its own mysteries, the enigmatic history and habitability of Venus. Now turning to the mysteries of Venus, often referred to as Earth's twin due to its similar size and proximity, we encounter a world that once might have been remarkably different from the hostile, scorching planet we know today. Venus today is a furnace with surface temperatures hot enough to melt lead and a thick atmosphere dominated by carbon dioxide, cloaked in dense clouds of sulfuric acid. Yet, evidence suggests that it may not have always been this way. Some scientists propose that Venus could have once harbored oceans of liquid water, potentially making it a habitable world billions of years ago. So, what caused this dramatic transformation from a potentially Earth-like planet to the hellish environment we see now? One of the prevailing mysteries is how long Venus may have maintained these oceans, if they ever existed, and what role they might have played in the planet's early geology and climate. Did Venus once have a stable climate with conditions suitable for life? Or were these oceans short-lived, doomed by the planet's proximity to the Sun and the onset of a runaway greenhouse effect? The runaway greenhouse effect is a process where the planet's atmosphere traps such an immense amount of heat that temperatures spiral out of control, turning the surface into the inferno we observe today. But the precise tipping point, the chain of events that led to Venus becoming uninhabitable, remains unclear. Adding to the intrigue are the mysterious highlands of Venus, which some researchers suggest could have been ancient tectonic plates, hinting that the planet might have experienced processes similar to Earth's plate tectonics in its early history. Plate tectonics play a crucial role in regulating Earth's climate by recycling carbon through the surface and interior, helping maintain stable conditions for life. However, whether Venus ever had a similar mechanism and how its surface geology evolved to become so starkly different from Earth's continues to challenge planetary scientists. Another puzzle lies in Venus's atmosphere. Despite its extreme conditions, Venus displays unexplained phenomena, including strange, dark patches in the clouds that absorb ultraviolet light. Some researchers speculate that these patches might be caused by unknown chemical compounds or, in an even more provocative hypothesis, microbial life adapted to the planet's harsh atmosphere. While evidence for life on Venus remains speculative at best, it underscores just how much we have yet to learn about our neighboring planet. The study of Venus is not only a quest to understand its mysterious past, but also a window into planetary evolution as a whole. By unraveling why Venus turned into such a hostile world, we might gain insight into the delicate balance required for a planet to remain habitable. Could Earth one day face a similar fate if certain tipping points in its climate system are crossed? These questions remind us of the fragile conditions that allow life to thrive and the cosmic forces that can so easily disrupt them. As scientists continue to send probes and develop missions to study Venus, the hope is that we can uncover more clues about its history and better understand the processes that govern planetary habitability. And with that, we now turn our gaze back to the universe at large, where magnetic fields weave through the cosmos, presenting yet another puzzle in our exploration of the ultimate unknowns. With the next phase of the journey in sight, we delve into the enigma of magnetic fields that permeate the cosmos, an invisible yet powerful force shaping the universe on every scale. From the magnetic field that shields our Earth, allowing life to flourish, to the immense magnetic structures threading through galaxies, their origin and organization remain profound mysteries. On Earth, our magnetic field is generated by the movement of molten iron within its core, a dynamo effect that creates a protective bubble called the magnetosphere. This shield deflects harmful solar radiation and cosmic particles, playing a crucial role in maintaining the conditions necessary for life. But when we extend our view outward, the picture becomes far more complex. Every planet with a magnetic field seems to create it differently. For instance, Jupiter's intense magnetic field, more than 20,000 times stronger than Earth's, is believed to be generated by metallic hydrogen swirling deep inside the gas giant. Yet not all planets have magnetic fields, and scientists are still piecing together why some worlds, like Mars, appear to have lost theirs entirely. Without a magnetic field, a planet becomes vulnerable to solar winds, which can erode its atmosphere and strip away the potential for habitability. But these planetary fields are just the beginning. Beyond individual planets, magnetic fields weave through entire galaxies and the vast expanse of intergalactic space. Galaxies like our Milky Way exhibit magnetic fields that stretch thousands of light years, following the spiral arms and even extending into interstellar space. The question is, how do these massive fields form and maintain such striking regularity? Some researchers propose that these galactic-scale fields might arise from the combined motion of charged particles over millions of years, amplified by dynamo processes similar to those within planets. However, this theory still does not fully account for their immense strength and order. Then there are the magnetic fields found in the chaotic cores of galaxy clusters and the vast voids of intergalactic space. These fields, weak yet pervasive, present one of the greatest puzzles of modern astrophysics. How can magnetic fields exist and remain coherent in such seemingly empty regions? Some theories suggest they originate from the early universe, seeded during the primordial moments after the Big Bang. Over billions of years, these initial magnetic fields might have been stretched and strengthened by cosmic events like galaxy mergers and supernova explosions, forming the large-scale structures we observe today. Yet, direct evidence for this process remains elusive. Adding to the mystery, these cosmic fields seem to influence the movement of charged particles throughout space, guiding high-energy cosmic rays as they travel vast distances. Even phenomena like the jets of material streaming from black holes at nearly the speed of light are thought to be shaped by intense magnetic forces. Despite extensive study, we are still far from understanding the true nature of these fields and their role in the grand tapestry of the universe. As scientists continue to investigate, the hope is that uncovering the secrets of these magnetic forces will not only deepen our understanding of the cosmos, but also shed light on the processes that govern everything from the formation of galaxies to the conditions that sustain life. With this magnetic mystery in mind, our journey across the unknown carries us forward to yet another enigma awaiting illumination. With the next phase of the journey in sight, we turn our attention to an icy phenomenon hidden in the distant corners of our solar system: ice volcanoes, or cryovolcanism, on dwarf planets. Unlike the fiery eruptions on Earth, where molten rock bursts to the surface, ice volcanoes expel a slushy mixture of water, ammonia, methane, and other volatile compounds. One of the most fascinating places to observe this is Ceres, the largest object in the asteroid belt, which has revealed peculiar dome-like structures scientists believe are ancient cryovolcanoes. The discovery of these geological oddities has raised profound questions about how a small, relatively cold world like Ceres could harbor the energy needed to drive such activity. On Earth, volcanic eruptions are fueled by the immense heat generated by our planet's molten interior and the movement of tectonic plates. In contrast, cryovolcanic activity on dwarf planets likely draws its power from a combination of residual heat from their formation, radioactive decay, and internal friction caused by tidal forces. This heat melts subsurface ice, creating a pressurized mixture of liquid and gas that eventually forces its way to the surface. When the mixture erupts, it freezes almost immediately in the frigid temperatures of space, leaving behind pancake-like domes or smooth plains of frozen material. But what makes this even more intriguing is that this process hints at the possibility of subsurface oceans or pockets of liquid water beneath the icy crusts of these small worlds. Such reservoirs could potentially harbor the conditions necessary for life, even in the most unlikely places. For instance, scientists have speculated that the cryovolcanism on Ceres might be linked to a briny liquid layer beneath its surface, akin to a salty underground ocean. This raises a tantalizing question. Could other icy moons or dwarf planets like Pluto or some of Saturn's moons exhibit similar phenomena? Cryovolcanism also provides clues about the geological and thermal evolution of these distant bodies, offering a glimpse into how they have managed to remain active despite their small sizes and vast distances from the Sun. The continuous reshaping of their surfaces suggests they are far more dynamic than previously thought, and yet so much remains unknown. How common are these icy eruptions in the solar system? What processes sustain them over potentially billions of years? And most importantly, what do they reveal about the hidden worlds lurking beneath their frozen exteriors? As we reflect on these icy eruptions from alien landscapes, it becomes clear that they redefine our understanding of planetary activity and the potential for habitability beyond Earth. With this chilling enigma fresh in our minds, let us venture onward to uncover yet another mystery that lies waiting in the cosmos. With the next phase of the journey in sight, we dive into the origins of our very own cosmic neighborhood, the Milky Way galaxy. Stretching over 100,000 light-years across and containing billions of stars, our home galaxy is a majestic spiral of stars, gas, and dust. But how did such an immense and intricate structure come into being? Scientists believe the story of the Milky Way began over 13 billion years ago, shortly after the universe itself was born in the Big Bang. At that time, small, dense regions of matter began collapsing under their own gravity, forming the first stars and galaxies. The Milky Way likely originated as a collection of these smaller proto-galaxies, which merged over billions of years, growing in size and complexity. One of the defining features of the Milky Way is its elegant spiral structure, with its arms stretching outward in a grand, swirling pattern. These spiral arms are not static. They are shaped and maintained by waves of gravitational energy, often referred to as density waves that ripple through the galaxy. Yet, despite these insights, much remains unclear. What triggered the formation of the spiral arms in the first place, and how do they remain so well defined for billions of years? Moreover, at the heart of the Milky Way lies a supermassive black hole, known as Sagittarius, a star, which is millions of times more massive than our Sun. Scientists are still unraveling how such a colossal black hole influences the galaxy's structure and evolution. Adding to the intrigue are the interactions the Milky Way has had with nearby galaxies. Over its long history, it has absorbed smaller galaxies in a cosmic process called galactic cannibalism, leaving behind streams of stars that now orbit in the outskirts of the galaxy. Even today, the Milky Way is on a collision course with the nearby Andromeda galaxy, and in about 4 billion years, the two will merge to form a massive elliptical galaxy. How these events shape not only the structure but also the star formation within the galaxy remains a profound mystery. The Milky Way's origins and evolution are closely tied to the vast web of dark matter that weaves through the universe. This elusive form of matter, which makes up most of the galaxy's mass, is thought to have acted as the cosmic scaffolding upon which the galaxy formed. Yet, because dark matter cannot be seen or directly detected, its role in the birth and growth of the Milky Way is still shrouded in mystery. As we study the Milky Way's spiral arms, its merging history, and the dark forces that shaped its existence, each discovery brings us closer to understanding not only where our galaxy came from, but also how galaxies across the universe evolve. With our gaze fixed on the stars within our home galaxy, let us now turn our attention to yet another vast and enigmatic phenomenon woven into the fabric of the cosmos. With the next phase of the journey in sight, we delve into one of the most perplexing phenomena in the cosmos, the Great Void. Imagine a region of space so vast and yet so empty that it defies our intuitive understanding of the universe. These voids, spanning hundreds of millions of light-years, contain far fewer galaxies, stars, and matter than the surrounding regions. One of the most famous examples is the Boots Void, a staggering expanse over 300 million light-years wide that holds only a handful of galaxies. But why do such immense cosmic deserts exist, and what do they tell us about the universe's grand structure? Scientists believe these voids are a natural result of the cosmic web, the large-scale structure of the universe. Shortly after the Big Bang, matter in the universe began clumping together under the influence of gravity, forming nodes of galaxies connected by filaments of gas and dark matter. Between these filaments, great empty regions were left behind, forming the voids we observe today. However, the sheer scale of these voids raises fundamental questions. Why are some of them so much larger and emptier than others? Could these colossal gaps hint at unknown processes in the early universe, or perhaps reveal something about the elusive nature of dark matter and dark energy? Another mystery lies in the role voids play in shaping the environment of galaxies near their edges. Galaxies on the outskirts of voids often exhibit unique properties, such as enhanced star formation or unusual movements. Could these peculiar traits be linked to the gravitational effects of the void itself, or are other forces at play? These questions remain unanswered. The Great Void's existence challenges our understanding of how the universe is organized on its largest scales. As we marvel at the vast emptiness of these regions, we are reminded of the delicate balance of forces that have shaped the cosmos into its intricate tapestry of galaxies, filaments, and voids. While the mysteries of these immense empty spaces continue to puzzle astronomers, they also offer a profound opportunity to understand the hidden forces that govern the universe. And as we navigate through the dark and light of the cosmic web, let us now shift our focus to another enigma that pushes the boundaries of our knowledge. With the next phase of the journey in sight, let us now explore the marvel of the most massive stars in the universe. Imagine a celestial giant so immense that it dwarfs our sun by hundreds of times in mass and shines millions of times brighter. Stars like R136A1, located in the Large Magellanic Cloud, represent the pinnacle of stellar extremes. This star, with an estimated mass of over 200 times that of our Sun, challenges everything we know about the limits of star formation and stability. But how can such enormous stars exist, and why are they so incredibly rare? Stellar giants like R136A1 form in regions of space dense with gas and dust, where the conditions are just right for gravity to compress material into massive protostars. However, these perfect conditions are an astronomical rarity, which is why these stars are so seldom seen. Even more fascinating is their fleeting lifespan. While our sun will burn steadily for billions of years, the most massive stars burn through their fuel at an astonishing rate, living for only a few million years before meeting a dramatic end. Their short lifespans contrast sharply with their brilliant existence, creating a cosmic balance between creation and destruction. But what determines their ultimate fate? For these colossal stars, the end is anything but quiet. Most will conclude their lives in supernova explosions, dispersing heavy elements into the surrounding space, which then contributes to the formation of new stars and planets. In some cases, their cores may collapse into black holes, leaving behind the most extreme remnants of their once great existence. Scientists are still unraveling the details of how these stars achieve such incredible magnitude and why their numbers are so limited. Are they a relic of an earlier, more chaotic universe, or do they form under very specific cosmic conditions that are difficult to replicate? These questions add to the allure of these massive stars, making them vital to our understanding of the life cycle of the cosmos. Stars like R136, A1 remind us of the universe's capacity for both grandeur and impermanence, as their brilliance illuminates the pathways to deeper cosmic truths. And as we reflect on these colossal wonders, let us turn our attention to one final cosmic puzzle, a phenomenon that intertwines chance and the mysteries of universal design. With the next phase of the journey in sight, let us delve into the fascinating realm of cosmic coincidences, those instances where the universe appears to align in ways that seem almost too perfect to be random. Take, for example, the remarkable alignment of the Sun and Moon during a solar eclipse. From our vantage point on Earth, the Moon is approximately 400 times smaller than the Sun, yet it is also about 400 times closer to us. This precise ratio allows the Moon to completely cover the Sun during a total solar eclipse, revealing the Sun's magnificent corona and creating a spectacle of awe-inspiring beauty. But how did this extraordinary alignment come to be? The odds of such a perfect match seem staggeringly low, leading some to wonder if there could be deeper, hidden forces at play. While scientists explain this alignment as a result of coincidental timing in the evolution of the Earth-Moon-Sun system, it still raises intriguing questions. For one, this alignment is not eternal. The Moon is slowly drifting away from the Earth at a rate of about 1.5 inches per year, meaning that millions of years into the future, such eclipses will no longer be possible. This fleeting nature adds a sense of urgency and uniqueness to the phenomenon, as though we are living in a cosmic moment that is both rare and transient. And eclipses are just one example of the many coincidences that seem to define our universe. Consider the fine-tuned conditions that allow for life on Earth, such as the precise distance of our planet from the Sun, or the delicate balance of forces that govern the cosmos at large. Are these coincidental, or do they suggest an underlying order or purpose woven into the fabric of existence? While science continues to probe these mysteries, the answers remain tantalizingly out of reach. Perhaps these cosmic alignments are not just chance occurrences, but clues pointing toward a deeper understanding of the universe and our place within it. As we ponder these thought-provoking phenomena, we are reminded that the universe is as much a source of questions as it is a wellspring of wonder, inspiring us to keep exploring, questioning, and reflecting on the intricate tapestry of existence. As our journey through these 50 cosmic mysteries comes to an end, one thing becomes abundantly clear: the universe is as boundless in its questions as it is in its marvels. From the enigma of the Great Attractor pulling galaxies toward an unseen destination, to the fleeting perfection of solar eclipses, to the possibility of multiverses, each mystery serves as both a puzzle and a source of awe. These unanswered questions remind us how much there is still to explore and inspire us to keep reaching for new understandings. Perhaps what makes these mysteries so captivating is not just the prospect of solving them, but the sense of wonder they ignite in each of us. So, what are your favorite cosmic mysteries? Which ones do you find the most mind-bending or thought-provoking? Let us know in the comments below. And if you enjoyed this cosmic adventure, be sure to subscribe to our channel, like this video, and hit the notification bell so you never miss a new exploration into the unknown. Together, let's continue unraveling the secrets of the cosmos, one mystery at a time. Thank you for watching, and until next time, keep looking up.